Close your eyes for a moment and imagine water. Perhaps you see a glass on your nightstand, condensation gathering on its surface. Maybe you hear rain tapping against your window, each drop a tiny messenger from the clouds above. Or perhaps you feel the memory of a cool stream flowing over your hands on a summer afternoon. Water is so familiar that it almost vanishes from our awareness. It waits quietly in every cell of your body. It shapes the weather beyond your walls. It carved the valleys and filled the oceans. It makes every breath, every thought, every moment of life possible. And yet, beneath this comfortable familiarity, water refuses to behave as it should. Its solid form floats when it should sink. It holds heat with stubborn persistence. Its molecules cooperate in ways that scientists still struggle to fully explain. Tonight, we're going to explore something extraordinary hiding in plain sight. Not a distant galaxy or a subatomic mystery, but the substance you drink every day. Because water's simple, ordinary. Everywhere water remains one of science's most beautiful unsolved problems. This isn't a story of what we don't know. It's a story of how something so completely studied can remain so deeply unfinished. How the familiar can still surprise us. How the ordinary contains infinite depth. So settle into your pillows, let your breathing slow, and prepare to see water as you've never seen it before. Not as a symbol or metaphor, but as a real physical marvel that helped science learn how to measure the universe, and continues to remind science of its limits. Welcome to Sleepy Science Tales. I'm so glad you're here tonight. This channel exists for moments like this when your mind is ready to rest, but still curious. When you want to learn something meaningful, but without the urgency or stress of daytime thinking. Here, science becomes a lullaby. Knowledge becomes comfort. If you're new to this journey, welcome aboard. And if you're returning, welcome back. You're part of a growing community of curious minds who believe that learning and resting aren't opposites, they're companions. Before we dive deeper into tonight's story, I want to ask a small favor. If you find yourself enjoying this gentle exploration, if the rhythm of these words brings you peace, would you consider leaving a like? It helps others discover this corner of the internet. And if you'd like more nights like this, more stories, that blend wonder with rest, the subscribe button is waiting for you. Along with the notification bell. Feel free to share this with anyone who loves science, who struggles with sleep, or who simply appreciates the beauty hiding in everyday things. And now, one more invitation in the comments below. Would you tell me where you're listening from tonight? Whether you're near an ocean, beside a river, in a place of rain or snow, or simply resting with a glass of water nearby, I'd love to know. There's something beautiful about people all over the world, united by curiosity, all thinking about the same molecule at the same moment. But enough from me. Let's begin. Water waits. That's perhaps the best way to describe its presence in our world. It waits in clouds, patient and suspended. It waits in underground rivers, moving through darkness. It waits in ice at the poles, holding records of ancient atmospheres. It waits inside you, making up roughly 60% of everything you are. This waiting is active, not passive. Water doesn't simply exist, it participates. It cools the engines we build. It softens the hardest stone over centuries. It carries heat from the equator to the poles. It dissolves minerals and transports them across continents. It shapes weather in ways we're still learning to predict. Children learn the word water early, often before they can spell it. We teach them that water is essential, that life needs it, that they should drink it regularly. But we rarely pause to ask why. Why is this particular arrangement of atoms to hydrogen, one oxygen, so special? Why does life depend on it specifically and not on some other liquid? The answer isn't simple, and that's what makes it beautiful. Water occupies an unusual position in science. It isn't unknown or mysterious in a dramatic way. It's not like dark matter, invisible and theoretical. It's not like consciousness, slippery and hard to define. Water is right here, measurable, reproducible, and extraordinarily well studied. And yet, ask a room full of physicists and chemists to explain all of water's properties. From first principles, and you'll find surprising disagreement. Not about whether water does certain things, that's settled, but about why. Precisely, it does them. About how all these strange behaviors connect. About what theoretical framework captures its nature most completely. This incompleteness isn't embarrassing. It's profound. Water has been examined by generations of the brightest minds in chemistry, physics, biology, geology, and planetary science. It's been measured, modeled, frozen, boiled, compressed, stretched, illuminated with lasers, and simulated on the world's most powerful computers, still, at its most fundamental level. Liquid water remains one of the hardest everyday materials to describe completely tonight. We're going to walk slowly through that puzzle, not rushing to solve anything, not pretending we have all the answers, but simply noticing how something so ordinary can remain so unfinished, how familiarity can hide complexity, how the universe doesn't owe us simple explanations, even for the things we touch every day. We'll move gently from what's firmly known into what's still debated. From molecules to planets, from structure to behavior, from certainty to honest uncertainty. There's no hurry here, no pressure to remember every detail. Just let the story wash over you like water itself, sometimes still, sometimes flowing, always present. Breathe slowly. Get comfortable. And let's begin where water's scientific story begins, not in a laboratory, but in an attempt to measure the world itself. Long before laboratories existed, before glass beakers and calibrated instruments, before universities and research journals, humans needed to understand matter in a way that could be trusted. They needed measurements that could be repeated in different places by different people and produce the same results. Water, simply by being everywhere and behaving consistently, became one of the first substances through which we learned how to measure the world. In ancient times, water was considered elemental, not a compound made of smaller parts, but a fundamental category of existence itself. Philosophers grouped it alongside earth, air, and fire. It was treated as something that simply was wet, flowing, heavy, seeking its own level. In this view, water didn't need explanation. It was explanation. This philosophical approach had a certain elegance, but it also created boundaries for curiosity. If water was elemental, why ask how it behaved internally? Why wonder about its inner structure? A shift began centuries later, particularly within the brilliant scientific traditions of the Islamic Golden Age. Scholars working across regions from Central Asia to North Africa began treating water differently, not as a philosophical given, but as a physical substance that could be quantified and tested. Al-Biruni, working around the year 1000, conducted careful measurements of density using water as his reference point. He compared equal volumes of different materials by observing how much water they displaced, producing values that remain remarkably accurate by modern standards. This wasn't philosophy. This was experimental method. Water had become a tool. Ibn Sina, known in the West as Avicenna, approached water from medical and physical perspectives. He described how it transferred heat, how it dissolved substances, how it affected bodily processes. Water became something whose properties could be observed and recorded, not assumed. What mattered in this shift wasn't that these scholars solved water's nature. They didn't. What mattered was that water became a stable reference point, something reliable enough to build other measurements around. As experimental science developed in early modern Europe, water's role expanded. When thermometers were first constructed, water played a central part. The freezing and boiling points of water under standard conditions became fixed markers on temperature scales, not because water was cosmically special, but because it was accessible, abundant, and behaved predictably enough to be useful. Mass standards followed similar logic. Early definitions of units, like the gram, were tied to specific volumes of water at specific temperatures. Water wasn't the object of study, it was the ruler by which other things were measured. This quiet role shaped scientific practice in ways we easily overlook today. Water trained generations of scientists to expect repeatability, to trust that measurements made in one place could be verified in another, provided the same reference was used. Even when Antoine Lavoisier helped establish modern chemistry in the late 1700s, recognizing that water wasn't elemental but a compound of hydrogen and oxygen, water's central position didn't diminish. If anything, it strengthened. Water became proof that complex behavior could arise from simple composition to lightweight gases, forming a stable liquid that did remarkable things. Yet even then, water's internal complexity was underestimated. Early atomic theory treated molecules as rigid little objects with fixed bonds and stable structures. Water fit neatly into diagrams and equations. What science didn't yet appreciate was that liquid water isn't a collection of isolated molecules sitting still. It's a constantly shifting network where bonds stretch, bend, break, and reform faster than the eye could ever see. Ironically, water's usefulness as a standard delayed recognition of its deeper complexity. Because it worked so well, it was easy to assume it was well understood. That assumption would persist quietly for a very long time. Imagine the surprise when scientists first realized that water, the most fundamental seeming substance, was not actually fundamental at all. For centuries, water had been treated as one of the basic building blocks of reality. Then came experiments with electricity. Scientists discovered they could pass electrical current through water and produce two different gases. One was flammable, burning with an almost invisible flame. The other made flames burn brighter and more intensely. Hydrogen and oxygen, two elements completely unlike water, somehow combining to create it. This discovery transformed chemistry. It showed that substances with entirely different properties could emerge when elements combined. Water wasn't just hydrogen plus oxygen in the way that a mixture of sand and salt is still recognizably both. Water was something new, a compound where the original elements lost their individual identities and created something with its own unique character. Henry Cavendish and Antoine Lavoisier, working in the late 1700s, helped establish this understanding through careful experiments. They weighed the gases that combined and the water that resulted. The ratios were consistent: 2 parts hydrogen to 1 part oxygen by volume, or about 8 parts oxygen to 1 part hydrogen by mass. This precision was thrilling. It suggested that matter followed exact rules, that nature operated through definite proportions, that the universe could be understood through measurement and reason. But here's where something subtle happened, something that would echo forward through centuries of water research. The discovery that water was how seemed to make it simpler. If you knew the parts, surely you knew the whole. Two hydrogen atoms bonded to 1 oxygen atom, arranged in a specific geometry. Problem solved, right? Not quite. Because knowing water's chemical formula is like knowing that a symphony is made of sound waves. True, but not explanatory. The formula tells you the ingredients, not why those ingredients produce water's specific, unusual properties. Why does water remain liquid at temperatures where similar molecules become gases? Why does ice float instead of sink? Why does water dissolve so many things? Why can it absorb so much heat without large temperature changes? The formula HEO doesn't answer these questions. It's a starting point, not an ending. As quantum mechanics developed in the early 20th century, scientists gained tools to understand chemical bonds more deeply. Walter Heitler and Fritz London showed in 1927 how electrons could be shared between atoms in stable ways, explaining bonds through probability clouds rather than fixed paths applied to water. These quantum insights revealed the molecules bent shape, not a straight line, with oxygen in the middle, but an angle of about 100.5 degrees. This geometry arises from how electron pairs repel one another around the oxygen atom. They also revealed water's polarity. Oxygen pulls electrons more strongly than hydrogen does, creating an uneven distribution of charge. One side of the molecule becomes slightly negative, the other slightly positive. This polarity turned out to be extraordinarily important. It meant water molecules weren't neutral little spheres, they were tiny dipoles, with built-in directionality, capable of sensing and responding to their neighbors. But even with quantum mechanics and precise measurements, something remained elusive. A single water molecule in isolation behaves one way. Put it with others and new properties emerge. Properties that belong not to individual molecules, but to the collective. This is where the story stops being about water's composition and starts being about water's Complexity. Because in your glass, in the ocean, in a cell, water molecules aren't isolated. They're intensely interactive, constantly coordinating, forming temporary associations, breaking them, forming new ones. Properties emerge from this restless coordination that you simply can't predict. By studying one molecule at a time, scientists realized they were facing something challenging, a many-body problem. Situations where the interactions between components matter just as much as the components themselves for water. This meant that the journey from HEO to understanding was much longer than anyone had anticipated. The formula was just the first step on a path that would lead through physics, thermodynamics, biology, and planetary science, revealing layer after layer of surprising behavior. Water had gone from element to compound, but it would take much longer to go from compound to comprehended, and even now, that last step remains incomplete. There's something quietly profound about how water became the standard, against which so much else was measured, not because anyone decided it should be special, but because it was simply there, accessible, consistent, universal. Let yourself imagine early laboratories centuries ago, candles providing light, hand-blown glass vessels holding liquids, careful hands recording observations in leather-bound notebooks. In these rooms, precision mattered enormously. Science was learning to be exact, learning to trust numbers, learning that careful measurement could reveal nature's patterns. Water anchored that learning. When thermometers evolved from crude devices to precise instruments, they needed fixed reference points. Temperature is, after all, somewhat abstract. It's the average energy of molecular motion, but you can't see or touch it directly. You need markers, reliable events that always happen at the same temperature. Water provided perfect markers, the temperature at which it freezes, and the temperature at which it boils. These phase changes, solid to liquid, liquid to gas, happen at consistent temperatures under standard pressure. They're sharp, observable, and reproducible. Different temperature scales were proposed, but almost all of them anchored themselves to water. Celsius defined 0 as water's freezing point and 100 as its boiling point. Fahrenheit chose different numbers but still referenced water's phase changes. Even the absolute Kelvin scale, which starts at the coldest possible temperature, connects back to water's behavior. This standardization had profound effects. A scientist in Paris and a scientist in London could report temperatures meaningfully to one another. A measurement made in winter could be compared to one made in summer. Precision became possible because water provided common ground. Mass measurements followed a similar path. The kilogram, one of the fundamental units of modern science, was originally defined as the mass of 1 liter of water at its maximum density, which occurs, interestingly, at about 4 degrees Celsius. Think about that for a moment. The standard for mass, the property we use to weigh everything from grains of rice to planets, was defined using water. This wasn't arbitrary. Water was abundant, purifiable, and stable. You could prepare a sample in Tokyo and trust it would have essentially the same properties as a sample prepared in New York. Purity itself became something judged relative to water. Distillation techniques were refined specifically to produce ever cleaner samples. If a laboratory could purify water effectively, removing dissolved salts and minerals, it demonstrated mastery of separation techniques that could be applied to other substances. Water trained science to expect repeatability. It fostered the idea that nature could be standardized, that experiments could be trusted across different locations and times if proper care was taken. This role continued even as chemistry matured and the classical elements were abandoned. Water retained its position. If anything, its importance grew. When Lavoisier established modern chemical nomenclature, identifying water as a compound rather than an element, it didn't lose status. Instead, it became an example of how simple components could produce complex, useful behavior. Throughout the 19th and 20th centuries, water remained central to research practice. Reactions were heated and cooled in water baths. Samples were dissolved, diluted, and transported in aqueous solutions. Biological specimens were kept viable in water. Geological processes were modeled using water flow. Water was the medium, the backdrop, the reliable constant. Scientific methods grew around its properties. Instruments were calibrated against it. Techniques assumed its availability. And here's the subtle irony: this very utility masked complexity. Because water worked so well as a reference, it was easy to assume it was simple. It became invisible in a way so familiar, so reliable, that its unusual nature faded into the background. Water was doing its job too well. It let science develop confidence in. Measurement before science was fully prepared to measure water itself. Only gradually did researchers begin to realize that their most trusted reference substance was also one of their least understood, that the liquid they used to calibrate everything else was resisting complete theoretical description, the standard. It turned out had secrets. Those secrets wouldn't reveal themselves through casual observation. They would emerge only when scientists began looking more carefully at what water actually did, at the molecular level, when they stopped treating it as a simple reference and started examining it as a complex system. And that's where the real surprises began. At first glance, water looks like the easiest possible puzzle. Take a slow breath and picture it: two hydrogen atoms, one oxygen atom, joined together in a small, tidy arrangement. No long chains like proteins, no branching complexity like sugars, no rare or exotic elements. Just three atoms, that's all, compared to the sprawling molecules of biology or the intricate crystals of minerals. Water seems almost modest, like a problem that should give up its secrets quickly, something you could solve over a weekend, or that a sufficiently clever graduate student could explain completely. For many years, scientists expected exactly that. In classical chemistry, molecules were imagined as tiny mechanical objects. Atoms were like beads connected by stiff wires. If you knew the parts and how they connected, the behavior should follow predictably. This approach worked surprisingly well for many substances, especially gases where molecules rarely interact, and solids where atoms sit in fixed positions. But water began to resist this simplicity as soon as anyone looked closely. The trouble starts with one simple fact: water molecules are never really alone. In a glass of water, you have something like 10 sextillion molecules. That's a 1 followed by 22 zeros. Each molecule influences its neighbors through electrical forces, brief quantum interactions, and something called hydrogen bonding that we'll explore more deeply soon. These interactions aren't especially strong individually, but there are so many of them, happening so constantly, that they dominate how water behaves. And here's where classical intuition fails: you can't just add them up linearly. The whole doesn't equal the sum of its parts. This is what physicists call a many-body problem. When you have two bodies, say, Earth and Moon, you can write down equations and solve them exactly, predicting orbits indefinitely. Add a third body and the mathematics becomes unstable, sensitive to tiny changes. Add trillions of bodies, all interacting, and exact solutions vanish entirely. Liquid water is exactly this kind of system. Each molecule forms temporary partnerships with several neighbors. When one connection forms, it changes the likelihood of others forming nearby. Networks appear, dissolve, and reappear on timescales of trillionths of a second. At any moment, some regions resemble ice, structured and orderly. Other regions look chaotic, disordered. Most exist somewhere between. These regions are tiny and short-lived, but they matter. They influence density, viscosity, how heat moves through the liquid, how sound travels through it. From a distance, water looks perfectly smooth and uniform. At the molecular level, it's restless, structured, and constantly reorganizing. Here's the remarkable thing: this restlessness isn't disorder. It's structure in motion. Water isn't failing to hold a shape. Motion is its shape. Quantum chemistry can describe how a few water molecules interact with impressive accuracy. Statistical mechanics can describe average behavior across billions of molecules. The challenge lies in the middle, in bridging individual quantum interactions and collective classical properties. This is why molecular simplicity doesn't guarantee behavioral simplicity. The rules don't disappear when you scale up. They multiply. They interact. They create feedback loops. A water molecule behaves one way in isolation. Place it in a cluster and its electronic environment changes. Place it in a dense liquid and its identity becomes inseparable from its constantly changing surroundings. Properties that seemed to belong to molecules turn out to belong to networks. And networks, unlike molecules, don't hold still. Water is simple only until it touches itself. Then it becomes a collective, responsive, constantly negotiating system. And that, it turns out, is where all the interesting behavior hides. Let's sit with this idea for a moment, this concept of many bodies interacting. It might sound abstract, but it touches something profound about how the universe works. Imagine a single dancer. You can predict their movements fairly well, where they'll step, how they'll turn, the arc of their arms. Now imagine two dancers. Still predictable, though they must coordinate, respond to each other, share space. Now imagine 1,000 dancers on the same floor, all moving at once, each one responding not just to their nearest neighbors, but to the shifting patterns of the whole group. Waves of motion ripple through the crowd. Formations emerge and dissolve. What any single dancer does depends on what everyone around them is doing, which depends in turn on their surroundings, creating loops of influence that cascade through the entire assembly. This is, in essence, what's happening in water, all the time, at speeds far beyond what we can see. In a system with just a few components, understanding usually builds from the bottom up. Learn the parts, learn how pairs interact, extend that to groups, and eventually you understand the whole. This reductionist approach has been one of science's most powerful tools, but in many body systems, this approach starts to buckle. The behavior of the whole genuinely isn't reducible to the behavior of the parts, because the parts keep changing what they're doing based on what everyone else is doing. Water molecules at any given instant are engaged in what you might call a negotiation. Each one is electrically polarized, slightly positive on one side, slightly negative on the other. They're constantly sensing the electric fields created by their neighbors and orienting themselves in response. These orientations aren't random, but they're not fixed either. They're probabilistic, dependent on temperature, on local crowding, on what happened a moment ago. The liquid explores possibilities continuously, settling into patterns that last just long enough to matter, then dissolving back into motion. What makes this especially challenging is that these interactions have memory, though not in the way we usually think of memory. When a molecule forms a hydrogen bond with a neighbor, it slightly changes that neighbor's electronic structure, which affects what that neighbor does next, which influences molecules further away. Information propagates through the liquid like ripples on a pond, except the pond itself is made of the ripples. Physicists have different ways of describing this. Some talk about correlation lengths, how far the influence of one molecule extends before it fades into noise. Others discuss relaxation times, how long it takes for a disturbance to settle down. Still others focus on cooperative phenomena where many molecules must move together for anything to happen. All of these perspectives are trying to capture the same essential truth. Water's behavior emerges from coordination across scales. Local structure matters. Medium-range organization matters. Long-range patterns matter. You can't isolate one level and understand the whole. This might sound frustrating, and in some ways it is, for scientists trying to build complete theories. But it's also beautiful, because what it means is that water is genuinely more than the sum of its parts. Emergent properties appear that no single molecule contains. The high heat capacity of water, its ability to absorb enormous amounts of energy without changing temperature, much doesn't exist in a single HEO molecule. It emerges from how millions of molecules coordinate their motion and share energy through their network of connections. Water's unusually high surface tension, that skin-like quality that lets insects walk on ponds, arises because molecules at the surface experience asymmetric pulling from neighbors below, creating a collective tension that individual molecules simply don't have. Even something as basic as water's density reflects cooperation. Molecules must collectively organize into patterns that occupy space efficiently, and those patterns shift depending on temperature and pressure in ways that isolated molecules couldn't predict. The many-body problem, then, isn't just a technical challenge. It's a window into how complexity works. How simple rules, repeated across vast numbers, create behavior that looks almost intentional, almost alive. Water demonstrates this daily, in every glass, every raindrop, every ocean wave. The complexity is always there, hidden in plain sight, waiting patiently for anyone curious enough to look closely. And once you see it, you can't unsee it. Water stops being background and becomes foreground, a participant in every process it touches. There's a beautiful asymmetry at the heart of every water molecule. Not a flaw, but a feature. A slight imbalance that changes everything. Picture that bent arrangement again, one oxygen atom with two hydrogen atoms attached at an angle. If charges were distributed evenly, this would be a neutral little system minding its own business. But oxygen is greedy for electrons. It pulls them more strongly than hydrogen does, creating an uneven distribution. One side of the molecule where oxygen sits becomes slightly negative. The other side where the hydrogens extend becomes slightly positive. Not a full charge like an ion, but a partial charge. The molecule becomes what we call a dipole, something with two poles, a directionality, an orientation. On its own, this might seem like a minor detail. Many molecules have slight charge imbalances. But in water, this polarity becomes transformative because of what happens when millions of these dipoles come together. Every water molecule is surrounded by other water molecules that are also unevenly charged. Each dipole feels the presence of its neighbors. They rotate, shift, and reorient in response, constantly adjusting to the local electric fields created by nearby molecules. This collective sensitivity gives rise to one of water's most important properties: its dielectric behavior, how it responds to and modifies electric fields. Water is exceptionally good at screening electrical forces. If you place two charged particles in water, they feel each other far less strongly than they would in air or vacuum. The reason is beautiful. Surrounding water molecules rotate, so their oppositely charged ends face the particles, partially cancelling their electric fields. This screening isn't passive. It's active, dynamic, and responsive. The liquid reorganizes itself continuously around charges, creating what scientists call a hydration shell, a responsive cloud of aligned molecules. Lars Onsager, a brilliant physicist working in the mid-20th century, helped clarify how these collective dipole interactions work. He showed that in polar liquids like water, long-range electrical effects arise not just from individual charges but from the cooperative response of many molecules acting together. The consequences ripple outward through chemistry and biology. Salts dissolve in water because the liquid stabilizes separated ions. When sodium chloride table salt enters water, positive and negative ions are pulled apart. Water molecules swarm around each ion, their dipoles oriented to provide electrical comfort. The energy benefit of this solvation overcomes the attraction between ions, allowing them to drift freely. Acids and bases behave differently in water for the same reason. Protons don't wander alone, they hop from molecule to molecule, through a constantly shifting network of hydrogen bonds. Water doesn't just host this movement. It actively participates, rearranging itself to enable proton transfer. Even neutral molecules are affected. Polar compounds dissolve readily because their charge distributions align compatibly with water's. Non-polar substances struggle because they disrupt local dipole organization without offering compatible interactions in return. The phrase "like dissolves like" captures this. Polar water welcomes polar guests and resists non-polar ones. In this way, water acts less like a neutral container and more like a collaborator. It's not simply the stage where chemistry happens, it's part of the performance, reshaping forces, altering reaction pathways, stabilizing intermediates. This responsiveness extends to larger scale organization as well, because water's dipoles interact over relatively long distances. Patterns of alignment can propagate through the liquid. These patterns are fleeting, existing for mere picoseconds, but they influence bulk properties, like viscosity and surface tension. Onsager emphasized that long-range order doesn't require rigid structure. Correlations can exist without permanence. Molecules don't need to lock into place to influence one another. Statistical alignment is enough, This is why water behaves coherently without becoming solid. At any moment, regions of the liquid exhibit partial alignment of dipoles. These regions form and dissolve continuously, shaped by temperature, pressure, dissolved substances. And nearby surfaces. The result is a liquid that senses and responds. Add salt and water reorganizes. Add heat and molecular motion disrupts alignment. Apply an electric field and dipoles rotate collectively. Place water near a surface and nearby molecules adopt preferred orientations. Water isn't indifferent, it reacts. This sensitivity allows water to support extraordinarily complex systems. Biological molecules rely on it to moderate forces that would otherwise be destructive. Charged groups on proteins remain stable because water softens their interactions. Cell membranes form because water reorganizes around nonpolar regions, effectively pushing them together. None of this requires intention. It arises purely from polarity interacting with density and motion. The uneven charge distribution of a single molecule scales upward to influence oceans, clouds, and living cells alike. What makes this remarkable is that the same underlying property explains phenomena across all these scales. The link isn't simple or obvious. Small changes in molecular alignment can lead to large shifts in observable behavior, but the connection is real and traceable. Water's polarity doesn't just explain why it dissolves salts or conducts electricity weakly. It explains why water can organize complex systems without freezing them into place, why it supports life's intricate chemistry while remaining chemically neutral itself. The imbalance never resolves. It persists, fluctuates, and propagates through every drop, every ocean, every cell. And in that persistent asymmetry lies much of water's quiet power. Now we come to something central, something that ties together almost everything unusual about water: the hydrogen bond. It's not a household name like gravity or DNA, but it's just as fundamental to the world you experience. Let your mind drift to ice for a moment, solid, crystalline, organized, then to steam, chaotic, dispersed, free. Between these extremes sits liquid water, and hydrogen bonding is what holds it there. In that narrow, precious middle state, a hydrogen bond is, in technical terms, a weak attraction between molecules, much weaker than the bonds holding atoms together within a molecule. But in water, these weak bonds appear everywhere, all the time, creating a network that gives the liquid its character. Here's how it works. Remember that each water molecule has a slight positive charge where its hydrogen atoms are, and a slight negative charge near its oxygen. These opposite charges attract. A hydrogen from one molecule is drawn toward the oxygen of a neighbor, not close enough to form a true chemical bond, but close enough to influence behavior. Each water molecule can participate in several of these bonds at once, donating hydrogen atoms to some neighbors while accepting bonds at its oxygen from others. The result is a loose, dynamic network extending throughout the liquid. Now here's the crucial part. These bonds are temporary. They last, on average, only about a picosecond, a trillionth of a second. Individual bonds constantly break and reform, usually with different partners. The network never stops rearranging. Early researchers tried to understand this by studying individual bonds and made good progress. Linus Pauling helped clarify the quantum mechanical basis of hydrogen bonding in the 1930s, showing it arose from electronic structure and favored specific geometries, and this is a big but. Knowing how a single hydrogen bond behaves doesn't explain what happens when trillions of them interact simultaneously. John, Desmond Bernal, and Ralph Fowler took a different approach in the 1930s. Rather than treating liquid water as disordered ice or compressed steam, they proposed it had its own kind of organization, not fixed, not crystalline, but patterned in a statistical sense. Their insight was that liquid water contains transient networks. Order exists, but it's probabilistic rather than deterministic. You can't point to a specific structure at a specific moment and say this is liquid water, but you can describe average tendencies, correlation lengths, typical connectivities. This distinction matters deeply. In a crystal, knowing one small region tells you about the whole structure. Patterns repeat precisely. In a gas, Molecules are so independent that each one's behavior is uncorrelated with others beyond brief. Collisions. Liquid water occupies the fascinating space between. Correlations exist. What one molecule does influences nearby molecules, but those correlations decay with distance and time. Order is local and temporary, yet persistent enough to matter. Think of it this way. Imagine a conversation at a party. Words flow, people speak and listen, thoughts are exchanged. There's structure, language, grammar, turn-taking, but it's fluid. The exact conversation couldn't be predicted in advance, yet it follows patterns. It has organization without fixity. That's liquid water, a conversation among molecules, governed by rules but never repeating exactly, structured but never static. Because of this, the hydrogen bond network responds smoothly to changing conditions. Increase the temperature and thermal motion disrupts alignment, bonds become shorter-lived. Average connectivity decreases. Lower the temperature and bonds persist longer, networks become more extensive. Approach freezing and the liquid begins to resemble ice, not suddenly, but gradually as local order becomes more pronounced. Pressure has its own influence. Compress the liquid and open structures favored by hydrogen bonding are squeezed into more compact arrangements. The balance shifts toward different configurations. Dissolved substances also matter. Ions and molecules distort the local network, either stabilizing certain patterns or disrupting them. The liquid adapts, reorganizing its bonding patterns to accommodate newcomers. This flexibility explains how water can dissolve so many substances while retaining its essential character. The network absorbs disruption without collapsing. It bends, rearranges, and continues. None of this is programmed. There's no master plan, no instruction set. Everything rises from local interactions repeated on an enormous scale. Yet collective behavior emerges stable, coherent, and remarkably robust. The hydrogen bond network gives rise to many of water's most familiar properties. Its unusually high boiling point for its molecular weight reflects the energy required to disrupt the network completely. Its surface tension arises because molecules at the surface experience asymmetric bonding, pulling them inward. Its high heat capacity comes from added energy going into rearranging bonds, rather than just increasing molecular motion. Each property emerges from cooperation. Importantly, this cooperation isn't perfect, it's noisy, incomplete, constantly in flux, and that imperfection is essential. A fully ordered hydrogen bond network would freeze into solid ice. A completely disordered one would vaporize into steam. Liquid water occupies the narrow space between, sustained by motion, held together by constant making and breaking of connections. This balance is difficult to capture mathematically, difficult to simulate completely, and difficult even to visualize. But it's the key to understanding why water behaves as it does. The network is everywhere water is. It doesn't have a shape you can draw, but it has profound influence. It's what makes water liquid, responsive, and alive in a chemical sense. And once you know it's there, this invisible, flickering network, you see its influence in everything water touches. Here's something worth pausing on. Order doesn't have to be permanent to be real. We usually think of order as static books ranged on a shelf, tiles in a pattern, atoms locked in a crystal. But water teaches a different lesson. Its order is like that of a murmuration of starlings. Thousands of birds wheeling through the sky in coordinated patterns that form and dissolve moment by moment. The order is undeniable, yet no single configuration lasts. This is what scientists mean when they talk about water's fluctuating order. At any instant, if you could somehow freeze time and examine a small volume of liquid water, you'd see regions with different characteristics. Some patches would have molecules arranged in nearly ice-like patterns, tetrahedral coordination, relatively open structure. Other patches would be more densely packed, molecules squeezed closer together, bonds at odd angles. Unfreeze time and these patches wouldn't stay put. The ice-like regions would melt into disorder. The disordered regions would develop structure. Everything would shift, blur, and reorganize within picoseconds. What's remarkable is that despite this constant turnover, average properties remain stable. Temperature stays constant. Density stays constant. The liquid doesn't suddenly become something else. This suggests that what matters isn't specific arrangements of specific molecules. What matters is the statistics of arrangements, how often certain patterns appear, how long they typically last, how they're distributed in space. Order becomes a matter of probability rather than position. This kind of order is harder to think about than crystal order, but it's not less real. In fact, it may be more common in nature, where the patterns fluctuate but of statistical regularity. Ecosystems change constantly but maintain characteristic structures. Even your thoughts arise from neurons that fire in patterns that are similar but never identical. Fluctuating order is order without repetition, structure without permanence, pattern without blueprint. Water demonstrates this beautifully because it operates on such fast timescales. The rearrangements happen too quickly for our senses to detect. We perceive stillness and uniformity where, at the molecular level, there's constant activity. This has practical consequences. Water's properties, like its ability to dissolve substances, conduct heat, or participate in reactions, depend on molecular environments that exist only briefly. A molecule might be in a perfect configuration for a particular reaction for only a few picoseconds. Then the moment passes, the structure changes, and the opportunity is gone. But another opportunity appears moments later, and another, and another. The transient becomes reliable through sheer repetition. Life exploits this. Enzymes create local environments where certain molecular arrangements become more probable. Chemical reactions depend on fleeting configurations appearing often enough to matter. Evolution has learned to work with water's fluctuating order, not against it. Understanding this kind of order requires shifting perspective. Less focus on what is where and more focus on what is likely, and for how long. Less concern with snapshots and more attention to movies, statistics, distributions. Water, by refusing to hold still, teaches science to think differently about what structure means. Order doesn't require stillness. Stability doesn't require permanence. Sometimes the most stable systems are the ones that never stop moving. Now we come to something so familiar you've probably never questioned it. Ice floats. Think about that for just a moment. Take a slow breath and really consider it. Ice in your drink bobs at the surface. Glaciers drift on oceans. Frozen lakes develop a lid of ice on top while fish swim below. This seems normal, but it's not. It's deeply strange. In most substances, the solid phase is denser than the liquid phase. Freeze something and its atoms pack together more tightly. Drop a solid chunk into the liquid form and it sinks. This is why solid wax sinks in melted wax. Why frozen carbon dioxide dry ice is denser than liquid CO2. Why most materials get heavier per volume when they solidify. Water does the opposite. And that difference shapes our entire world. As liquid water cools from room temperature, it behaves normally at first, contracting, becoming denser as molecules slow down. But around 4 degrees Celsius, something unexpected happens. Instead of continuing to contract, water starts to expand. As it approaches freezing, this expansion accelerates. When water finally solidifies into ice, the volume increases by about 9%. That might not sound dramatic, but at the scale of lakes and oceans, it's enormous. The reason lies in hydrogen bonding. As water freezes, those temporary hydrogen bonds become more stable and persistent. Molecules lock into position, but not in a dense arrangement in an open one. Ice forms a hexagonal lattice that maximizes hydrogen bonding at the expense of packing efficiency. Picture a crowd of people holding hands. They can stand close together with arms at odd angles, or they can step apart into a more spacious formation where everyone's arms extend comfortably. Ice chooses the spacious option. It prioritizes bond geometry over density. Liquid water, by contrast, is messier and paradoxically more compact. Its hydrogen bond network constantly rearranges, allowing molecules to slip into spaces that would be forbidden in ice's rigid structure. The result: solid water is less dense than liquid water. Ice floats. Now consider what this means. When a lake freezes in winter, ice forms at the surface. That ice layer acts as insulation, slowing further heat loss from the water below. Life beneath the ice survives in liquid water even as air temperatures plunge far below freezing. If ice sank, the situation would be catastrophic. Freezing would begin at the bottom. Ice would accumulate on the lake floor, harder to melt when spring arrived. Over successive winters, many bodies of water would freeze solid from bottom to top. Aquatic life as we know it would be impossible in seasonal climates. This single property ice floating enables winter survival for countless species. It stabilizes ecosystems across vast regions of the planet, but the strangeness goes deeper. Water's density maximum at Celsius, not at freezing point, creates seasonal circulation patterns in lakes. Cool water sinks until it reaches for sea, then it starts rising again as it cools further. This circulation moves nutrients, distributes oxygen, and influences entire aquatic ecosystems. Water's expansion upon cooling also shapes geology. When water seeps into cracks in rocks and freezes, it expands, exerting tremendous pressure. Over time, this force fractures even the hardest stone. This process, called frost wedging, contributes to soil formation and landscape evolution. Glaciers carve valleys. Ice sheets shape continents, all because frozen water floats and expands beyond Earth. This matters too. On icy moons like Europa and Enceladus, ice layers floating on subsurface oceans may insulate those oceans from the cold vacuum of space, allowing liquid water to persist beneath miles of ice. If water behaved like most substances, if ice sank, many of these worlds would look very different. Their oceans might freeze solid. Habitability would be less likely. So ice floating isn't a quirky detail. It's a structural signature of how hydrogen bonding works, scaled up to planetary significance. A simple molecular preference for certain bond angles creates a property that influences climate, ecology, geology, and potentially even the distribution of life in the cosmos. All because water expands when it should contract. All because solid is lighter than liquid. All because molecules choose comfort over density. Familiar, yes. But once you see how strange it really is, that familiarity begins to look like a kind of miracle. Let's stay with this expansion idea a moment longer, because it reveals something profound about how water balances competing forces. Most materials expand when heated and contract when cooled. The logic is straightforward. Add energy, molecules move more vigorously and need more space. Remove energy, molecules settle closer together. Simple, predictable, linear. Water, especially near its freezing point, refuses this simplicity. As mentioned, water reaches its maximum density around for sea. Cool it further and instead of getting denser, it expands. Heat it from that point and it also expands. The density maximum sits right in the middle, a peak rather than a plateau. This behavior is called negative thermal expansion in the region below for sea. It's unusual, not unique, but rare among common substances. The underlying cause is that ongoing competition between structure and entropy. Hydrogen bonding favors open, organized arrangements. Thermal motion favors dense, disordered packing. Temperature determines which tendency wins. At higher temperatures, thermal motion dominates. Molecules jostle energetically, bonds break often, and the liquid remains relatively compact. As temperature drops, hydrogen bonds become more influential. They start directing molecules into more spacious, ice-like configurations even before actual freezing occurs. Below for sea, this structural preference overcomes the tendency to contract and water expands. What's beautiful is the balance. Not too hot, where structure vanishes. Not too cold, where motion stops. Right at the edge where both factors contribute significantly. This balance has consequences. In oceans, this density maximum affects circulation. Water cooled at the surface sinks until it reaches for sea. Cool it further and it becomes buoyant again. This creates layering and influences how heat and nutrients are distributed vertically. In lakes, autumn cooling causes turnover as surface water reaches for Celsius and sinks, bringing nutrients from the depths. This mixing event is crucial for aquatic ecosystems, effectively resetting the system before winter ice formation. Water's expansion near freezing also means ice formation starts at the surface, rather than throughout the volume simultaneously. If water contracted normally all the way to freezing, supercooling would be more common, leading to rapid, chaotic freezing events instead. The expansion provides a smooth transition. Liquid water near 0 Celsius becomes increasingly structured, gradually taking on ice-like character before crossing the phase boundary. This gentleness, this gradualism is unusual. Phase transitions are often sharp and abrupt. Water's density anomaly softens the transition, spreading it across a temperature range. The same principle applies under pressure. Compress water and its behavior shifts again. At high pressures, different balance points are reached, and entirely new ice phases appear, some denser than liquid water, violating the familiar floating rule. Percy Bridgman's early 20th century experiments revealed this by subjecting water to extreme pressures. He discovered multiple forms of ice, each stable under specific conditions, each with distinct structures and properties. The phase diagram of water, rather than being simple, branches into complexity. Ice floating is just one outcome within a broader landscape of possibilities. Under different conditions, higher pressure, different temperatures, water adopts other solutions to the problem of how to arrange molecules energetically. What remains constant is the competition. Hydrogen bonding versus entropy, structure versus motion, order versus density. The competition never resolves. It shifts depending on conditions, creating different manifestations, but always present, always shaping behavior. Negative thermal expansion near freezing is one visible expression of that underlying tension, a reminder that water's familiar properties arise from delicate balances that could, under slightly different circumstances, tip entirely differently. That we live in a world where ice floats is, in a sense, contingent, not inevitable, but arising from the specific way hydrogen bonding strength compares to thermal energy. Under Earth-like conditions, change the parameters slightly and water might behave entirely differently. The substance we depend on would be something else. Fortunately for us, the balance sits exactly where it does. Water does something remarkable with heat. It absorbs it quietly, holds it patiently, and releases it slowly. This property might sound mundane, but it shapes everything from your body temperature to global climate. Let's explore this gently. Imagine heating a pot of water on a stove. Now imagine heating an equal mass of cooking oil, or alcohol, or most other liquids. The water takes longer, noticeably longer to warm up. It's as if water resists temperature change, buffering against it. Scientists quantify this using specific heat capacity. How much energy is required to raise 1 gram of substance by 1 degree? Water's specific heat capacity is unusually high, roughly 4 times that of many other common liquids. Where does all that energy go if not immediately into temperature, into relationships, into the breaking, bending, and rearranging of hydrogen bonds? When you add heat to water, much of that energy is absorbed by the network itself, changing bond angles, disrupting local structures, enabling molecular rearrangement. Temperature, remember, reflects average kinetic energy, how fast molecules are moving. But in water, added energy doesn't only increase molecular speed, it also goes into changing how molecules interact, how they're organized, how the network is configured. This creates a buffer. Energy input is partially stored in structural changes rather than purely in motion. Temperature rises more slowly as a result. Think of it like this. If you give money to someone who's debt-free, they can spend it all immediately. But if you give money to someone paying off debts, much of it goes toward obligations before they have spending money. Water's hydrogen bond network is like those debts. Energy goes into servicing the network before being free to increase temperature. From a thermodynamics perspective, this relates to entropy, the distribution of energy within a system. In many materials, adding heat rapidly increases entropy by increasing randomness of motion. In water, entropy increases more gradually because energy is diverted into reorganizing interactions. This moderation has profound effects. Large bodies of water resist rapid temperature change. Oceans absorb enormous amounts of solar energy during the day and release it slowly at night. Seasonal temperature swings are softened. Coastal regions experience milder climates than inland areas at similar latitudes. Your body, which is roughly 60% water, uses this property for temperature regulation. Water in your cells and bloodstream absorbs metabolic heat without large temperature spikes. When you sweat, evaporating water carries away substantial heat, cooling you efficiently. On a planetary scale, water stabilizes climate, without oceans absorbing and redistributing heat. Temperature extremes between day and night, summer and winter. Equator and poles would be far more severe, but the influence goes deeper than weather and physiology. Ilya Prigogine, a brilliant physical chemist, explored systems that exist far from equilibrium systems that maintain organization by continuously exchanging energy with their surroundings. Living organisms are prime examples. They're not in equilibrium. They're sustained by constant energy flow. Water's thermal properties enable such systems to exist stably, because water can absorb and release heat without wild temperature swings. It provides a stable thermal environment for far from equilibrium processes. Energy can flow through steadily rather than violently. Gradients can be maintained without immediate collapse. Consider a living cell. Metabolic reactions generate heat. If that heat weren't managed, temperature would rise rapidly, disrupting delicate chemistry. Water, comprising most of the cell's mass, absorbs that energy and redistributes it. Temperature remains stable even as thousands of reactions proceed simultaneously. The same principle scales upward. In oceans, heat absorbed at the surface is transported by currents, redistributed across vast distances over long time scales. Energy enters, moves, and leaves without destabilizing the system. This ability to stabilize dynamic systems is one of water's most important, but underappreciated roles. It doesn't eliminate instability, it manages it. It allows systems to exist in dynamic balance, neither frozen nor chaotic, persistently active. From a thermodynamic view, water mediates between energy input and system response. It slows transitions, spreads them out in time, and allows gradients to persist without breaking down immediately. This mediation works across scales. At molecular scales, hydrogen bonding absorbs energy. At larger scales, bulk motion and convection distribute heat. At planetary scales, oceans and ice regulate energy exchange with space. All these processes link together, creating a multi-scale thermal buffer that stabilizes conditions across Earth's surface. Entropy still increases, thermodynamics isn't violated, but the path entropy takes is shaped by water's properties. Disorder is produced gradually, channeled through manageable flows rather than released in bursts. This has deep implications for how complexity arises and persists. Complex systems require both stability and change. To rigid, and they can't adapt. To chaotic, and they can't maintain structure. Water provides a middle way. It permits constant motion without catastrophic transitions. It supports energy flow without destroying organization. There's no drama here, no sudden shifts. Just a quiet, persistent moderating influence that makes dynamic order possible. Heat enters water, moves through it, and eventually leaves, but the journey is patient. And in that patience, worlds become possible: chemical worlds, biological worlds, conscious worlds, all because one small molecule makes heat wait. This heat-holding capacity connects to something broader, a concept worth settling into. Thermodynamic buffering. Let yourself imagine water as a mediator between extremes, not preventing change but softening it, not eliminating fluctuation, but spreading it across time. In systems where water is abundant, sudden shifts become gradual transitions. Sharp boundaries become smooth gradients. Abrupt changes become gentle slopes. This buffering appears in countless contexts. When weather systems form, water vapor in the atmosphere acts as a thermal reservoir. Condensation releases heat slowly, sustaining storms and weather patterns. Evaporation absorbs heat, cooling surfaces and moderating temperature. In soil, water content determines how quickly temperature changes with depth. Wet soil resists temperature swings more than dry soil. Plant roots experience more stable conditions as a result. In bodies, human, animal. Plant water comprises most of the mass and dominates thermal behavior. Core temperature stays within narrow ranges despite external fluctuations. And internal heat generation from metabolism. Even in industrial processes, Water's heat capacity is exploited for cooling, heating, and temperature control. From power plants to kitchens, water's thermal properties make it an invaluable working fluid. But beyond practical applications, there's something conceptually important here about how water enables stability in dynamic systems. Prigogine emphasized that many interesting systems, including living things, exist far from equilibrium. Equilibrium is stasis, death. Life requires persistent disequilibrium maintained by constant energy flow. Water provides the medium where such disequilibrium can persist safely. It doesn't prevent energy flow. It regulates it. It doesn't freeze change. It distributes change over time and space. Think of a river. Water flows continuously, carrying energy from higher to lower elevations. The flow is steady, not catastrophic, because water's properties mediate how energy is released. Waterfalls demonstrate potential energy conversion, but even there, water cushions the impact, dissipating energy through turbulence and spray rather than explosive release. Now scale this up to an entire planet. So, let energy pours onto Earth's surface constantly. Oceans absorb a substantial fraction, storing it in thermal form. This heat is redistributed by currents released gradually to the atmosphere, and eventually radiated to space. Without water's thermal buffering, day-night temperature swings would be extreme. Seasonal shifts would be violent. Climate zones would be harsher. Biological systems would face constant thermal stress. Water doesn't prevent these fluctuations. Earth still has seasons, weather, climate variations, but it softens them enough that adaptation becomes possible. Evolution has time to work. Ecosystems can stabilize. Life can persist across changing conditions. In this way, water is a regulator at planetary scale. Not through active control, but through passive properties: high heat capacity, efficient energy transport, phase changes that absorb and release energy at consistent temperatures. None of this is intentional. Water doesn't try to stabilize anything. It simply behaves according to its physical and chemical properties. And those properties happen to create stabilizing effects. There's a quiet beauty in that. No purpose required. No design necessary, just the emergent consequences of hydrogen bonding and molecular geometry, scaled up through sheer abundance. Thermodynamic buffering, then, is less about preventing change and more about making change manageable. Water buys time. It spreads disturbances across space. It converts abrupt shifts into gradual adjustments. And in that moderation lies the foundation for much of the organized activity we see, from biochemistry to weather. From cellular metabolism to ocean circulation. Water creates breathing room, gives systems time to respond rather than react, allows complexity to persist in a universe that tends toward equilibrium. It doesn't stop the flow toward disorder. It just makes the journey longer, gentler, and full of possibilities along the way. And that, in the deepest sense, is what enables the richness of our water-rich world. Now let's push water somewhere it rarely goes in everyday experience, under extreme pressure. What happens when you squeeze water hard, really hard? Not the modest pressure of ocean depths, but the crushing forces found deep inside planets. At first, familiar ice appears. Then, as pressure increases, something fascinating happens. Ice doesn't simply compress into a denser version of itself. Instead, it transforms into entirely different crystalline structures, different phases, each stable under specific conditions. Scientists have discovered more than a dozen distinct forms of ice. Each has its own arrangement of molecules, its own density, its own properties. Some are denser than liquid water, violating the familiar rule that ice floats. Others have unusual electrical or mechanical characteristics. These discoveries came largely from Percy Bridgman's pioneering work in the early 20th century. He developed techniques to subject materials to extreme pressures, revealing that ice's phase diagram branches and complexifies rather than simplifying under stress. Why does this matter? Because it reveals water's underlying flexibility. The same hydrogen bonding that gives us familiar ice can reorganize itself in fundamentally different ways when conditions demand it. Push even further into pressures millions of times atmospheric. Combined with high temperatures and something even stranger emerges: superionic ice. In this exotic state, Oxygen atoms form a relatively fixed lattice while hydrogen ions move freely through it, almost like a fluid passing through a solid. This is not metaphor, it's a distinct phase where the material is simultaneously solid. And liquid-like, superionic water conducts electricity efficiently. It forms under conditions so extreme, they seem irrelevant to daily life pressures found deep within ice giant planets, like Uranus and Neptune. But here's why it matters. These planets likely contain vast amounts of water in superionic form. This affects their magnetic fields, internal heat flow, and structure. Understanding water in this regime helps us understand planetary interiors. Throughout the solar system and beyond, extreme conditions also reveal which interactions truly matter. When you compress water enough, the comfortable assumptions about molecular identity start to blur. Hydrogen bonds shorten dramatically. Electronic structures shift. New physics becomes relevant. Studying water at extremes isn't just cataloging weird states. It's stress testing theory. Models that work at room temperature and pressure may fail under compression. Understanding why they fail sharpens understanding overall. There's also an important philosophical point here. Water's familiar behavior is contextual. Ice floating is true under Earth's surface conditions, but not universal. Water's properties are shaped by the specific temperature and pressure ranges we happen to inhabit. Change the context and water changes with it. The adaptability that allows liquid water to rearrange constantly at room temperature is the same. Adaptability that allows solid water to adopt multiple crystalline forms under pressure. Water doesn't have a single nature. It has a range of possible behaviors, and which one manifests depends on conditions. This theme will echo through the rest of our journey. Water is not one thing. It's a system with many faces, and understanding it means understanding how those faces emerge from underlying flexibility. Let that idea settle as we move into even broader territory. Let's pull back now, widen the lens, and see water not as isolated molecules, but as a planetary participant, a substance woven into Earth's very functioning. For a long time, scientists studied Earth's components separately. Oceanographers studied oceans. Atmospheric scientists studied air. Geologists studied rocks. Biologists studied life. Each discipline had its own methods, journals, and paradigms, but gradually, a different view emerged. Earth as a system, an interconnected whole where atmosphere, ocean, ice, land, and life influence one another through countless feedback loops. And water cycling through all these domains sits at the heart of these connections. James Lovelock, working with Lynn Margulis, helped popularize this system's view through what became known as Gaia theory. While some interpretations became metaphorical, the scientific core is straightforward. Earth's surface environment stays within habitable ranges, not through accident, but through feedbacks that link physical, chemical, and biological processes. Water participates in many of the strongest feedbacks. Consider temperature regulation. As Earth warms, more water evaporates into the atmosphere. Water vapor is a greenhouse gas trapping heat. This creates a positive feedback. Warming leads to more water vapor, which leads to more warming. But other feedbacks counteract this. More evaporation also means more clouds. Depending on their altitude and type, clouds can reflect sunlight back to space, cooling the surface. They can also trap heat, warming it. The net effect varies, creating complex, context-dependent regulation. Water in its frozen form, ice and snow, creates another powerful feedback. Ice reflects sunlight efficiently, keeping surfaces cool. If ice melts, darker land or ocean is exposed, absorbing more solar energy and accelerating warming. This ice-albedo feedback amplifies changes in either direction. Yet water also participates in stabilizing feedbacks over longer time scales. Rainfall weathers rocks chemically. Slightly acidic rainwater reacts with silicate minerals, consuming atmospheric carbon dioxide and producing dissolved ions that rivers carry to the ocean. In the ocean, these ions eventually form carbonate sediments, locking carbon away for millions of years. This weathering feedback provides long-term climate stability. If CO2 levels rise, greenhouse warming increases. That accelerates rainfall and weathering, which removes CO2, eventually moderating the warming. It's a slow process operating over tens of thousands to millions of years, but powerfully stabilizing. Water, by flowing across continents, links the atmosphere, land surface, and ocean in this carbon regulation cycle. Without liquid water, this stabilizing feedback would be vastly weakened. Oceans themselves are massive reservoirs of heat and carbon. They absorb roughly a quarter of human CO2 emissions and an enormous fraction of excess heat. Ocean circulation redistributes this heat globally, moderating regional climates. The slow overturning circulation where warm surface water flows poleward, cools, sinks, and returns at depth operates over centuries. This sluggishness introduces inertia into the climate system, resisting rapid shifts, ice sheets. 2. Respond slowly. Their immense mass requires centuries to millennia to grow or shrink substantially. This introduces another form of inertia, preventing abrupt climate transitions. All these processes unfold on vastly different timescales. Weather operates over days, ocean currents over decades to centuries, ice sheets over millennia, rock weathering over millions of years. Water participates in all of them, weaving together fast and slow processes into a multi-scale regulatory system. This doesn't mean Earth's climate is perfectly stable or immune to change it demonstrably. Isn't. But it means that over geological time, despite massive external changes, variations in solar output, asteroid impacts, continental drift, liquid water has persisted on Earth's surface for billions of years. That persistence reflects the cumulative effect of countless water-mediated feedbacks. From hydrogen bonds to planetary circulation, the same substance participates continuously. Its physical chemistry doesn't stop at the molecular level, it echoes upward through scales. Shaping flows, cycles, and feedbacks, water becomes more than a component of the planet. It becomes a connective tissue linking domains that might otherwise remain isolated. Not a controller, not a designer, but a regulator whose influence emerges from motion, interaction, and time. The planet doesn't hold water still. Water moves through the planet, and in that movement, it quietly helps determine how the planet evolves. It's a partnership forged not by intention, but by physical law playing out over 4 billion years. And understanding that partnership requires seeing water not as a substance, but as a process threaded through the living earth. Water's relationship with life is often described as essential, obvious, necessary. But there's something subtler happening that's worth appreciating. Water doesn't instruct chemistry to become biological. It creates conditions where chemistry can explore widely without immediately failing. In other words, water is permissive, it enables without directing. This distinction matters when thinking about how life began. Early ideas imagined a straightforward progression, simple molecules form, combine into complex ones, eventually something living appears. Water in these stories was background, a convenient solvent where things happen to occur. Alexander Oparin, working in the 1920s and 30s, challenged that simplicity. He proposed that life emerged through extended chemical evolution in aqueous environments. Water wasn't merely a container, it was the environment that allowed complexity to accumulate and persist long enough to matter. Early Earth was chemically rich and physically dynamic. Energy flowed through the system from sunlight, geothermal heat, electrical storms, radioactive decay. Water connected these energy sources to reactive molecules, allowing them to mix, collide, and reorganize. Crucially, water didn't favor particular outcomes. In an aqueous environment, countless reactions can proceed simultaneously. Some products are stable, others decompose quickly. Many pathways are explored and abandoned. Water allows this exploration by moderating energy and stabilizing intermediates. This open-endedness is essential. If chemistry were to constrain, only narrow reaction sets would be possible. If to chaotic, complex molecules would be destroyed as fast as they formed. Water occupies the middle ground, supporting reactions while buffering extremes. One way it does this is through solvation. When molecules dissolve in water, they become surrounded by oriented water molecules that stabilize charges and lower energy barriers. Reactions that would be difficult in dry environments become feasible in water. At the same time, water discourages certain arrangements. Nonpolar molecules tend to cluster not because they attract each other strongly, but because water reorganizes around them to minimize disruption. This hydrophobic effect drives assembly without encoding specific structures. The result is a chemically permissive environment where many molecular architectures can form, persist briefly, and interact. Modern prebiotic chemistry research supports this. Experiments simulating early Earth conditions show that water supports formation of sugars, amino acids, nucleotides, and simple lipids under plausible conditions. None guarantees life, but together they create a chemical landscape rich with possibility. Hydrothermal vent research adds further nuance. Deep beneath oceans where seawater meets hot rock, steep chemical gradients form. Alkaline hydrothermal vents particularly resemble environments where life might have started. These vents produce natural proton gradients across mineral membranes similar to gradients modern cells use to drive metabolism. Water is essential here, transporting dissolved gases, moderating temperature, and participating directly in reactions at mineral surfaces. These environments are far from equilibrium. Energy flows continuously. Matter cycles through multiple states. Water provides the medium that keeps processes stable enough to persist, without immediately equalizing. What's striking is that even in focused settings, water doesn't push chemistry towards single outcomes. Different vent systems produce different mixtures. Slight changes in temperature or composition lead to divergent results. This introduces contingency outcomes depending on specific histories and conditions, not just universal laws. Water supports contingency by remaining flexible. Because it doesn't rigidly fix molecular arrangements, multiple pathways can coexist. Molecules assemble, disassemble, reassemble differently. Structures form temporarily, break apart, reform another way. This contrasts sharply with environments where chemistry is tightly constrained. On solid surfaces, structures may lock in place. In highly viscous media, exploration slows. In water, exploration continues. This doesn't mean life was inevitable. The very openness of aqueous chemistry suggests life was one possibility among many. Water provided opportunity, not destiny. Once biological systems emerged, water's role shifted subtly. It continued enabling diversity, but biology added specificity. Proteins fold into precise shapes. DNA stores information. Membranes form controlled boundaries. These structures depend on water's properties but impose constraints water alone doesn't provide. Even here, water remains a partner rather than a director. Protein folding is driven by the hydrophobic effect, water's preference to maintain its hydrogen bond network, but the final shape is determined by the protein's sequence. Enzymatic reactions rely on water to stabilize charges and transfer protons. But specificity comes from enzyme structure. Life exploits water's permissiveness while adding layers of control and specificity on top. Water supports biological complexity without defining it. Understanding this helps avoid misconceptions. Water didn't make life happen by itself, nor did life arise despite water. Life emerged within a chemical environment flexible enough to explore complexity, and stable enough to preserve it. That balance is rare, precious, and on Earth sustained for billions of years, allowing chemistry to try countless experiments. Water keeps the laboratory open. Now we come to one of biology's most beautiful puzzles: how proteins fold. If you've seen images of proteins, you know they look intricate ribbons twisting into elaborate three-dimensional sculptures, each one seemingly designed for its specific task. But here's the mystery: proteins aren't sculpted by anyone. They fold themselves. A protein starts as a linear chain of amino acids, sometimes hundreds long, linked together in a specific sequence. On its own, that chain has no obvious shape. It can bend and twist in countless ways. If folding were truly random, exploring all possible configurations would take longer than the age of the universe. Yet inside cells, many proteins fold reliably in seconds. How? The puzzle was highlighted by Cyrus Leventhal in the 1960s. But an even deeper insight came earlier from Walter Kaufmann in the 1950s. Kaufmann focused on what became known as the hydrophobic effect. Here's the paradox he noticed. Nonpolar parts of amino acids don't attract each other strongly. So why do they cluster together inside folded proteins, hiding from water? The answer is beautiful and indirect. It's not about the nonpolar groups pulling together. It's about water pushing them away, or more precisely, water preferring not to organize around them. When nonpolar surfaces are exposed to water, surrounding water molecules lose some freedom to form hydrogen bonds optimally. This costs energy. When nonpolar groups come together, burying themselves inside the protein, surrounding water becomes freer to organize comfortably. The system as a whole becomes more stable. Protein folding, then, is driven not by the protein pulling itself together, but by water shaping what arrangements are energetically favorable. The solvent influences the outcome without specifying it. This is indirect causation beautiful, subtle, and easy to miss. Understanding this shifted how scientists think about folding. Rather than imagining a specific pathway leading to a final structure, researchers now think in terms of energy landscapes. Picture a rugged funnel. Many configurations exist at higher energies near the top. As folding proceeds, the chain moves downhill toward lower energy, guided by interactions with water and with itself. There may be local valleys where the chain pauses or misfolds temporarily, but overall the slope leads towards stable forms. Importantly, this landscape is shaped by surrounding water. Change the solvent and the landscape changes. Proteins that fold easily in water may not fold at all in other liquids, or may adopt entirely different shapes. The folding problem cannot be separated from the medium in which it occurs. This is why studying proteins in isolation often fails. In vacuum, they behave very differently. Charged groups interact too strongly. Structures collapse or distort. The balance provided by water disappears. Water screens electrical charges, moderates attractions, and penalizes exposure of nonpolar surfaces. It creates constraints that guide folding without micromanaging it. This guidance is subtle. No single water-protein interaction determines final shape. Instead, millions of fleeting interactions collectively bias the system towards certain configurations. Once folded, proteins aren't rigid. They breathe. Side chains wiggle. Loops shift. Even stable structures fluctuate constantly. These motions aren't noise, they're essential for function. Enzymes need flexibility to bind substrates and release products. Structural proteins must absorb stress without breaking. Signaling proteins often switch between shapes depending on their environment. Water participates in all this motion, filling cavities, stabilizing transient charges, absorbing energy from conformational changes. Without water, the delicate balance between stability and flexibility would be lost. This highlights something important. Protein folding isn't about finding a single perfect shape. It's about finding a family of shapes that are stable enough to persist and flexible enough to function. Water supports this balance. The hydrophobic effect ensures nonpolar regions are generally buried, but not permanently locked away. Hydrogen bonding with water stabilizes polar regions while allowing rearrangement. Electrostatic screening prevents charges from dominating structure. Together, these influences create robust systems without brittleness. This robustness underlies biological complexity. Living systems depend on large numbers of proteins interacting in crowded, noisy environments. Mistakes happen. Conditions change. Temperatures fluctuate. Chemical concentrations vary. Despite this, function persists. Water plays a central role in this resilience, cushioning interactions, absorbing disturbances, allowing exploration of small variations without catastrophic failure. Even misfolding, often seen as purely problematic, reflects this flexibility. Proteins can adopt alternative structures under stress. Some misfolded states are reversible. Others are managed by cellular machinery. The system adapts. From a chemical standpoint, none of this is obvious. A long chain of amino acids should behave unpredictably. That it doesn't is a consequence of indirect causation mediated by water. Water doesn't tell proteins how to fold. It makes certain foldings energetically comfortable, leaving room for variation. This is a powerful recipe for complexity. At a deeper level, protein folding illustrates a general principle. Complex biological behavior often arises, not because components actively enforce order, but because the environment makes some arrangements easier than others. Water shapes the landscape. Proteins navigate it, and from that navigation emerges the intricate machinery of life. Simple? No. Elegant? Absolutely. And once again, water achieves this not by imposing design, but by quietly shaping possibility, making some paths easier, others harder, and leaving biology to find its way inside a living cell. Water is everywhere, but it's not all the same. A cell isn't a simple bag of liquid. It's a crowded, structured environment packed with proteins, membranes, nucleic acids, and molecular machines. Water still makes up most of the mass, but much of it is confined, influenced, or structured by nearby surfaces. This raises an important question. Does water inside cells behave like bulk water, or does it take on different properties? The careful answer is, some aspects are well established, others remain contested. One idea that's generated discussion comes from Gerald Pollack, who proposed the existence of what he calls exclusion zone water regions near certain surfaces, where water adopts more ordered structure, excludes dissolved particles, and may carry different electrical properties. Laboratory experiments have shown that near some surfaces, particularly charged or hydrophilic ones, dissolved particles are indeed pushed away over distances larger than expected. These exclusion zones can extend tens or even hundreds of micrometers under certain conditions. This observation is real and reproducible in some experimental setups. Water near surfaces does behave differently from water far away. Where debate begins is in interpretation. Does this represent a distinct phase of water, fundamentally different from ordinary liquid? Or is it a gradual structural gradient that's more pronounced under specific conditions? Most physical chemists and biophysicists agree on a narrower point. Water near interfaces is structured. Its properties differ from bulk water. Hydrogen bonds may be more ordered. Molecular motion may be restricted. Electrical behavior can be altered. What's less clear is how far these effects extend, how stable they are under physiological conditions, and how dominant they are in living cells. Cells are dynamic. Proteins move. Membranes flex, ions flow. Water is constantly displaced, reorganized, and exchanged. Any structured region must exist within this restless environment. Experimental ambiguity is almost unavoidable here. Measuring water structure often relies on indirect methods: spectroscopy, scattering, magnetic resonance that provide averages over many molecules and timescales. Interpreting these signals requires models, and different models can fit the same data. This isn't experimental failure. It's a limitation imposed by scale. Inside cells, water molecules interact with surfaces every few nanometers. There's very little space where water behaves as it would in a beaker. In that sense, intracellular water is almost always interfacial, making the idea of structured water near surfaces unsurprising. What matters is degree, not existence. Another distinction lies between structural influence and functional significance. Even if water near surfaces is partially ordered, does this ordering play a major role in cellular processes? Or is it simply a background condition cells have adapted to? Evidence remains mixed. In many cases, observed effects can be explained using conventional electrostatics, hydration shells, and crowding models without invoking distinct water phases. This doesn't make the questions unimportant. It highlights the need for precision. One reason these discussions attract attention is that water inside cells challenges simple assumptions. Textbooks often imply cellular chemistry occurs in dilute aqueous solution. In reality, cells are densely packed. Free water is limited. This crowding alters reaction rates, diffusion, and molecular interactions. Water mediates all of it. Near membranes, molecules align with charged head groups. Near proteins, they form hydration shells that stabilize structure and facilitate motion. Near nucleic acids, they screen charges along the backbone. These effects are well supported experimentally. Where interpretation becomes speculative is when local ordering is assumed to propagate over large distances or dominate cellular behavior. Most evidence suggests structured water regions are local, transient and sensitive to conditions. Temperature, ionic strength, and molecular composition all matter. Scientific caution is warranted here. Water inside cells is heterogeneous, its properties vary depending on proximity to surfaces, charge distributions, and crowding. Some degree of structuring near interfaces is measurable and real. Claims of large scale, long-lived alternative phases remain unproven but worth continued investigation with better tools and clearer questions. Let's return to that hydrophobic effect we touched on earlier, because it reveals something profound about how water organizes. Complexity without instructions. The word hydrophobic literally means water-fearing, and it's applied to molecules or molecular regions that don't dissolve well in water, oils, fats, the waxy coating on leaves. But here's the thing, these molecules don't actually fear water. They're not repelled by it. What happens is subtler and more interesting. When non-polar molecules enter water, they disrupt the hydrogen bond network. Water molecules nearby can't form hydrogen bonds as easily with each other, so they adopt somewhat awkward configurations to maintain as much network as possible around the intruder. This costs energy, not a lot per molecule, but it adds up. The system as a whole becomes less favorable. Now, when two non-polar molecules come together, the amount of water surface in contact with non-polar material decreases. Water can reorganize more comfortably. The overall energy of the system drops. So non-polar molecules appear to attract each other, but they're actually being pushed together by water's preference to maintain its own structure. It's indirect, elegant, and surprisingly powerful. This hydrophobic effect drives many self-assembly processes in biology. Cell membranes, for example, form because lipid molecules have a nonpolar tail and a polar head. In water, the nonpolar tails cluster together, hiding from the solvent, while polar heads face outward. This spontaneous organization creates the bilayer structure that defines cell boundaries. No blueprint required, no assembly instructions, just molecular components responding to water's organizational preferences. Proteins, as we discussed, fold partly because their nonpolar amino acids bury themselves inside, away from water. This isn't the only force involved, but it's a major one, arguably the dominant one in many cases. Protein-protein interactions often involve nonpolar surfaces coming together again, driven by water's influence rather than direct attraction between proteins. Even larger structures, molecular complexes, cellular compartments often rely on hydrophobic effects to achieve and maintain organization. What's remarkable is that water accomplishes all this organization passively. It's not actively pushing or pulling. It's simply maintaining its own hydrogen bond network as best it can, and in doing so, it creates environments where certain molecular arrangements become energetically favorable. This is organization through constraint rather than construction. Water doesn't build anything. It shapes what's possible and what's unlikely, and lets molecules find their own arrangements within those constraints. There's an important principle here that extends beyond chemistry. Indirect causation can be just as powerful as direct force. Sometimes the most effective way to create order is not to impose it from outside, but to create conditions where order emerges naturally. Water does this continuously, at every scale where it's present, from membranes to proteins to cellular structures. Its influence is everywhere, not through active intervention, but through providing an environment with specific preferences. Life has evolved to exploit these preferences. Biology didn't have to teach water how to organize non-polar molecules. Water was already doing that. Evolution simply had to discover molecular sequences and structures that work with water's tendencies rather than against them. In that sense, life is a conversation with water, a partnership where one side provides organizational principles through its physical chemistry, and the other side explores what's possible within those principles. Neither side is in control. Both participate, And from that participation, astonishing complexity emerges. The hydrophobic effect, then, is not just a chemical phenomenon, it's a demonstration of how simple preferences, applied consistently across countless interactions, can generate the organized structures that make life possible, all because water wants to maintain its hydrogen bond network. That's it. That simple preference, scaled up, becomes a creative force, and once you see it that way, water's role in life shifts from background to foreground, an active partner in every biological process, shaping outcomes without ever giving orders. Beautiful, don't you think? Now we come to a challenge that runs through all water research, the problem of measurement itself. Trying to measure water at the molecular level is like trying to photograph a murmuration of starlings while everyone is constantly changing position. By the time you capture an image, the moment has already passed. At the scale where water's character emerges, nothing holds still. Hydrogen bonds form and break in trillionths of a second. Molecules rotate, vibrate, and translate continuously. Local structures appear and dissolve faster than most instruments can track. Any attempt to observe water risks averaging away the very behavior that makes it interesting. For much of scientific history, this limitation was invisible. Early measurements focused on static properties: density, boiling point, heat capacity. These quantities are averages, and averages hide motion. As understanding deepened, it became clear that water's defining features lie not in static structure, but in dynamics, in how things change over time. This shifted the challenge from locating molecules in space to tracking how long they stay there, where they go next, and what influences those movements. Many traditional techniques provide excellent spatial detail but blur time. X-ray diffraction excels at revealing ordered structures in crystals. But liquid water doesn't crystallize. When short-range order exists, it fluctuates too quickly to be captured cleanly. Spectroscopic methods, infrared, Raman, nuclear magnetic resonance offer valuable insights by probing how water absorbs and emits light at specific frequencies. But here again, interpretation depends on time scale. A signal that appears stable may be the average of rapid fluctuations. The importance of time was brought into sharp focus by Omid Zewail's work in the late 20th century. He developed techniques using ultrafast laser pulses to observe chemical reactions on time scales of femtoseconds, quadrillionths of a second. At these time scales, atoms can be seen moving, bonds can be observed forming and breaking. Transient states that were once purely theoretical become measurable, applied to water. Ultrafast spectroscopy reveals a world in constant flux. Hydrogen bonds stretch and collapse within a few hundred femtoseconds. Vibrational energy flows through the network almost immediately. Local arrangements flicker in and out of existence. These observations confirm what theory suggested: liquid water isn't a static assembly. It's a dynamically reorganizing system whose properties emerge from motion. Yet even ultrafast techniques have limits. To observe something, you must perturb it, deposit energy, apply a field, introduce a probe. That perturbation alters the system, however briefly. This introduces an observer effect especially pronounced for water. Because water is so responsive, even small perturbations can shift hydrogen bonding patterns. The act of measurement risks changing what's being measured. Different techniques emphasize different aspects of water's behavior. Neutron scattering is sensitive to hydrogen positions but averages over time. Infrared spectroscopy captures vibrational dynamics but requires careful modeling to translate signals into structure. Nuclear magnetic resonance provides information about mobility and environment, but often lacks spatial specificity. Each method offers a partial view. Combining techniques helps, but introduces complexity. Data from different experiments must be reconciled. Models are required to bridge gaps, and assumptions creep in. This is where the moving target becomes a modeling problem. Experimental measurements produce signals that must be translated into molecular descriptions. If models are incomplete or biased, interpretation follows suit. For water, this is a persistent challenge. Models that reproduce bulk properties may fail at interfaces. Models capturing hydrogen bonding accurately may struggle with long-range correlations. The result is a patchwork understanding not from lack of effort. Water is among the most intensively studied substances, but from inherent difficulty. Water moves too fast, interacts too complexly, and responds too sensitively to be captured completely by any single technique or model. The moving target doesn't settle. It just becomes more detailed as methods improve. When experiments struggle to keep up with motion, scientists turn to simulation. If water can't be held still long enough to measure cleanly, perhaps it can be recreated inside a computer-calculated molecule by molecule, interaction by interaction. This idea has driven decades of work in molecular modeling, producing remarkable progress alongside persistent disagreement. At the heart of most simulations lies molecular dynamics, atoms treated as particles, moving according to forces between them. Positions and velocities are updated repeatedly over tiny time steps, allowing the system to evolve. Success depends entirely on how those forces are described, what scientists call force fields. A force field specifies how strongly atoms attract or repel one another, how bonds stretch and bend, how charges interact. For water, this includes parameters for bond lengths, angles, partial charges, and hydrogen bonding behavior. Force fields aren't derived directly from first principles. They're constructed with parameters chosen to reproduce certain known properties: density, diffusion rate, heat capacity, dielectric behavior. If a model matches these targets well, it's considered successful. But success is selective. A force field tuned to match bulk properties may fail at interfaces. One optimized for room temperature may perform poorly under extreme pressure. This isn't a flaw in execution, it reflects the fact that no finite set of parameters can capture all aspects of a system as complex and responsive as water. Different force fields disagree. Simulations using different models can predict different hydrogen bond lifetimes, different degrees of local order, different responses to temperature and pressure. All may appear reasonable, all may reproduce some experimental data, yet they don't converge on a single picture. This has led to long-standing debates. One axis of disagreement lies between empirical modeling and approaches driving interactions more directly from quantum mechanics, often grouped as ab initio modeling, meaning calculations based on fundamental principles rather than fitted parameters. Density functional theory plays a central role here. It describes how electrons distribute within a system, allowing interactions to be calculated from electronic structure rather than imposed by parameter choice. In principle, this is more rigorous. In practice, it introduces its own approximations. The exact form of electron interaction isn't known, so must be approximated using functionals. Different functionals emphasize different aspects. No single choice is universally correct. Ab initio simulations are also computationally expensive. Simulating large volumes of water for long times remains difficult. Trading scale for detail. This creates tension. Empirical force fields can simulate millions of molecules over long times, but rely on assumptions. Ab initio methods capture electronic effects more faithfully, but at cost of system size and duration. Neither approach can claim complete authority. What complicates matters further? Models are judged by how well they reproduce experimental observables, but as we've seen, experiments themselves depend on interpretation and averaging. A model may match one experiment while contradicting another. Agreement with data doesn't guarantee correctness of mechanism. Two models can reproduce the same average behavior for different reasons. Without direct access to underlying motion, it's difficult to decide which representation is closer to reality. This is where assumptions quietly accumulate. Every model encodes choices about what matters and what can be ignored. Should hydrogen atoms be treated explicitly or averaged? Should polarization be fixed or responsive? Should quantum effects be included or approximated classically? None of these decisions is neutral. They shape outcomes in ways that aren't always obvious. When different groups make different choices, disagreement follows naturally. These disagreements aren't signs of confusion, they're signs that water sits near the limits of current modeling approaches. Unlike a rigid solid or dilute gas, liquid water occupies a regime where interactions are strong enough to matter, but weak enough to fluctuate. Collective behavior emerges from many small effects. Capturing this accurately requires balancing detail and tractability, a balance that remains elusive. As computational power increases, models grow more sophisticated. Polarizable force fields allow charges to respond to environment. Machine learning approaches attempt to infer interaction patterns from large datasets. Hybrid methods combine quantum and classical descriptions. Each advance improves some aspects while introducing new questions. This leads to philosophical implications. What are models meant to do? Are they literal representations of reality, or practical tools reproducing selected behaviors? Should a model predicting observables accurately be preferred? Even if its internal picture seems artificial, there's no single answer. In water science, models often serve as hypotheses proposing how the system might behave, constrained by known principles and data. Experiments then test consequences. Seen this way, modeling water is less about convergence on final description, and more about mapping a space of possibilities, each model highlighting certain mechanisms, together building composite understanding. This perspective helps explain why debate persists even after decades of work. Water doesn't yield easily to single frameworks. It resists reduction to minimal rules, and perhaps that's a valuable lesson in itself. Let's be clear about something. Water's status as an unsolved problem doesn't mean it's poorly understood. On the contrary, water is one of the most thoroughly studied substances in existence. The unsolved aspects lie deeper, in questions about unification rather than description. Liquid water occupies an unusual position in physics. It's everywhere, endlessly useful, and studied in extraordinary detail. Yet within condensed matter physics, it remains one of the clearest examples of a problem that refuses to close completely. The reason is structural. Solids are well understood because atoms occupy fixed positions and vibrate around them. Gases are tractable because particles interact weakly and briefly. Both extremes allow clean theoretical descriptions. Liquids sit between atoms, are close like solids but constantly rearranging like gases. Interactions are strong enough to matter yet transient enough to evade simple treatment. This intermediate character makes liquids difficult to generalize. Among all liquids, water stands out as especially resistant to simplification. Philip Ball has explored this tension extensively in his synthesis of water research. His work emphasizes that water's difficulty is genuine. It sits at the edge of what current theoretical frameworks handle well. One reason: liquids lack a unifying theory. For solids, lattice models provide common language. For gases, kinetic theory offers statistical framework. For liquids, no equivalent universal description exists. Each liquid must often be treated on its own terms using approximations tailored to its interactions. Water complicates this further by combining several competing tendencies. Hydrogen bonding promotes local order. Thermal motion disrupts it. Electrostatic interactions extend over longer ranges. Molecular geometry enforces directional constraints. None dominates completely. The system balances on the edge between structure and disorder. This balance produces intermediate states at any moment. Regions resemble ice. Others resemble disordered fluid. Most exist somewhere between. No sharp boundary separates them. The liquid samples all configurations continuously. These intermediate states matter because they influence measurable properties: density anomalies, compressibility, heat capacity. Response to pressure all depend on how populations of local structures shift with conditions. The difficulty lies in describing this shift rigorously. In crystals, phase transitions involve clear changes in symmetry. In gases, changes are smooth and predictable. In liquid water, transitions are blurred. Structural motifs fade in and out rather than appearing or disappearing sharply. This makes it hard to define relevant degrees of freedom. Should water be described in terms of individual molecules, hydrogen bond networks, clusters, density fluctuations? Each description captures something real. None captures everything. Experimental evidence supports this ambiguity. Scattering reveals short-range order but no repeating pattern. Spectroscopy shows vibrational modes heavily broadened by motion. Thermodynamic measurements reveal anomalies but don't uniquely specify microscopic origin. Multiple interpretations coexist. Some models emphasize tetrahedral order inherited from ice. Others highlight density fluctuations resembling those near critical points. Some propose to interconverting liquid-like states at low temperatures. Others argue such distinctions are unnecessary. Each view is supported by some evidence, challenged by other data. This would be uncomfortable if water were obscure. It's the reference liquid against which others are compared. That sharpens the problem. Condensed matter physics often relies on simplification, seeking minimal models capturing essential behavior. Water resists reduction. Remove hydrogen bonding and anomalies vanish. Remove electrostatics and structure dissolves. Remove motion and the liquid freezes. What remains is not water. This resistance has philosophical implications. It challenges the idea that understanding necessarily converges on single elegant descriptions. It suggests some systems may require layered explanations, each valid within its domain. Liquid water appears to be such a system behavior emerging from interactions that are individually simple but collectively intricate. No single interaction explains properties. No single scale dominates. This places water among frontier problems, not mysterious dramatically, but sitting at boundaries of existing theory. Water's status as unsolved doesn't mean it's unknowable. It means knowledge takes a different form consisting of constraints, patterns, tendencies, and limits rather than single equations or models. Understanding consists of knowing what's possible, what's likely, what's excluded. Scientists know a great deal about what water does, its anomalies, phase behavior, role in life and climate. Predictions are often reliable. What remains unsettled is not water's behavior, but water's unification, why anomalies cluster together, how local order propagates, whether behavior can be unified within broader theoretical framework for liquids. These questions point toward limits of knowledge rather than gaps, easily filled by more data. Recognizing these limits is itself understanding. It allows science to proceed without illusion that every system must yield tidy summary. Water, after all, doesn't behave badly. It behaves consistently with its nature as densely interacting, multi-scale system that nature simply doesn't lend itself to single settled account. And perhaps that's the lesson. Some of the most familiar substances reveal sharpest boundaries of explanation, not because they're exotic, but because they sit where simplicity gives way to complexity. Let's sit with a big idea for a moment. Complexity, not as a vague term for difficult, but as a specific concept about how nature organizes itself. Complexity theory studies systems made of many interacting components whose collective behavior can't be predicted simply by analyzing each part alone. These systems are often non-linear, small changes producing disproportionate effects. Cause and effect not neatly proportional. Liquid water fits this description remarkably well. Each molecule follows simple physical laws. Interactions between pairs are well characterized. Yet when trillions interact simultaneously, behavior isn't a straightforward sum of interactions. This is emergence, patterns and properties arising at collective levels that don't exist at component levels. In linear systems, doubling input doubles output. Understanding parts leads directly to understanding wholes. In non-linear systems like water, doubling input can leave output unchanged, amplified unexpectedly, or inverted entirely depending on context. Water demonstrates this across many properties. Small temperature changes near freezing produce expansion instead of contraction. Minor pressure shifts produce new structural arrangements. Slight composition variations alter large-scale behavior. Murray-Gell-Mann explored such phenomena through complex adaptive systems. While his work spanned physics, biology, and information theory, the central idea applies here. In complex systems, patterns emerge from interaction, feedback, and adaptation rather than centralized control or simple rules. Water isn't adaptive biologically, but its hydrogen bond network continuously responds to local conditions. Bonds form where energetically favorable, dissolve where not. Patterns adjust dynamically. The system reorganizes without instruction. This responsiveness makes reductionism stall. Reductionism breaking systems into components has been extraordinarily successful in science, revealing atomic structure, molecular bonding, genetic codes. But reductionism assumes understanding smallest parts will eventually explain the whole. With water, that assumption reaches limits. Knowing everything about isolated water molecules doesn't explain liquid water's properties. Knowing about pairs doesn't explain networks. Even knowing about local clusters doesn't fully determine large-scale behavior. Each level introduces new interactions, new patterns, new properties. This doesn't mean reductionism is wrong, just incomplete when used alone. Water demands complementary approaches focusing on collective behavior and interaction across scales. One way to see this: at what scale does water become water? Is it at individual molecules? Those behave very differently in isolation. At hydrogen-bonded pairs? Those are fleeting. At clusters? Those constantly rearrange. There's no single scale where water's defining properties suddenly appear. They emerge gradually across continua. This lack of privileged scale is unusual. Many systems have clear levels where behavior stabilizes, lattices in crystals, statistical ensembles in gases, cells in organisms. Liquid water has no such anchor. Properties depend on correlations extending over multiple scales simultaneously. Local hydrogen bonding influences intermediate range structure, which influences macroscopic properties like density and heat capacity. None of these levels can be ignored. None dominates completely. This scale-free character complicates theory. Models must choose which scales to emphasize. Emphasize local structure and long-range correlations may be missed. Emphasize bulk averages and subtle structural motifs vanish. Each choice captures part of truth, obscures another. This is why decades of study have produced refinement rather than closure. As tools improve, water appears more intricate, not less, from complexity theory's perspective. This is expected. Complex systems don't yield single final explanations. They're better understood through multiple overlapping descriptions, each valid within domains. This reframes what it means to understand water. Rather than seeking definitive models explaining everything, scientists increasingly aim to map regimes of behavior under these conditions. These approximations work. Under those, others apply. Transitions between regimes become objects of study themselves. Water becomes a system of context rather than single object. This also explains persistent expert disagreement. Different researchers focus on different scales, phenomena, questions. They build models suited to their goals. Those models may not align perfectly because they were never meant to. Disagreement here is information. Signaling water can't be compressed into single explanatory frame without loss. There's temptation to see this as failure to complete the story. In reality, it reflects field maturity. Simple problems are solved early. Difficult ones remain. Water sits at intersections of many disciplines: physical chemistry, condensed matter physics, statistical mechanics, biophysics, geophysics, planetary science. Each brings useful tools. None has final authority. This interdisciplinary position slows convergence but prevents premature closure, keeping multiple perspectives alive. At deeper levels, water challenges an often unexamined assumption that nature must be describable in simple unified terms at every scale. Complexity theory suggests otherwise. Some systems may be irreducibly complex, their behavior can't be compressed. Without losing essential features, this doesn't mean unknowable. It means knowledge takes different form: constraints, patterns, tendencies, limits. Water demonstrates this beautifully. Scientists know what water does, can predict many outcomes reliably. What remains unsettled is unification, the why beneath the what, and recognizing that distinction is itself a form of understanding. Push water far enough beyond everyday experience, and it reveals even more faces, reminders that what we call water is really a family of related behaviors, each emerging under specific conditions. We touched on this briefly earlier, but it's worth dwelling on. Water under extreme pressure doesn't simply compress uniformly. It discovers entirely new ways to range itself. As pressure increases through regimes far beyond ocean depths, into pressures found only deep within planetary interiors, water ice transforms repeatedly. Each transformation produces a distinct crystalline phase with its own structure, density, and properties. Scientists have catalogued more than a dozen ice phases, each stable within specific temperature-pressure windows. Some are denser than liquid water, others have exotic electrical or mechanical characteristics. Push further still into pressures millions of times atmospheric combined with high temperatures, and you reach supersonic ice, a phase where oxygen atoms form a relatively fixed lattice, while hydrogen ions move freely through it like a fluid within a solid. Supersonic water conducts electricity efficiently. It forms under conditions so extreme they seem irrelevant to daily life pressures deep inside planets like Uranus and Neptune. But understanding water in this regime helps explain planetary magnetic fields, internal heat flow and structure. The unusual magnetic fields of ice giants tilted and offset from centers may be influenced by conductive supersonic water layers deep within in astrophysics. Water's extreme behavior informs models of exoplanets. Many discovered worlds are larger than Earth but smaller than gas giants. Their interiors may host vast quantities of water in unfamiliar phases. Habitability, magnetic shielding, geological activity all depend on how water behaves there. Even in cosmology, understanding water at extremes touches fundamental questions about matter itself. Phase diagrams taught as tidy maps turn out to be branching trees. New limbs appear as conditions extend. Boundaries blur. States overlap rather than converging toward simplicity under stress. Water's diagram expands, revealing new possibilities. This is a recurring theme. Pushing water to extremes doesn't eliminate anomalies, it reveals new ones. The value lies not only in cataloging phases but understanding principles. Which interactions dominate under compression? How does hydrogen bonding adapt? When does molecular identity persist and when does it dissolve? Extreme conditions act as stress tests for theory. Models working near ambient conditions may fail under pressure. Assumptions break down. New behaviors demand explanation. In this way, extremes drive discovery, showing water's familiar properties aren't isolated quirks but manifestations of deeper flexibility. The same tendencies causing ice to float also allow supersonic forms to exist. The same hydrogen bonds structuring liquid water reorganize under pressure into entirely new architectures. This continuity across conditions is striking, suggesting water's behavior can't be understood by focusing solely on comfortable middle ground. Its full character emerges only when examined across entire range of possibilities. Extreme studies also provide perspective. Earth's oceans occupy narrow, fortunate niche within water's broader phase space. Liquid water at moderate temperature and pressure isn't the default state of the universe. It's one option among many. That realization sharpens questions about water's role elsewhere. If water exists in so many forms, which ones matter for life, geology, planetary evolution? Which behaviors are essential, which incidental? Exploring extremes doesn't answer directly, it frames questions by revealing how water behaves. When pushed far from familiar, science gains leverage on why ordinary behavior is special. Not because it's unique, but because it sits at crossroads of competing tendencies. Science gains leverage on why ordinary behavior is special. Not because it's unique, but because it sits at crossroads of competing tendencies. Water under extreme conditions isn't oddity, it's continuation. Each phase discovered expands understanding rather than closing it. From laboratory compression to planetary interiors, water remains adaptable, intricate, surprising. Understanding it at extremes isn't detour from understanding it here, it's part of the same story, unfolding across scales. Now let's widen the lens even further beyond Earth, beyond our immediate neighborhood into the broader cosmos where water plays. Roles we're only beginning to understand. Water didn't originate on Earth. That's not philosophy, it's chemistry. The hydrogen and oxygen making up water were forged in different astrophysical settings long before planets existed. Hydrogen emerged in the universe's earliest moments. Oxygen formed later inside stars, released through stellar winds and supernova explosions. Water itself assembled wherever conditions allowed those elements to meet and bind. Understanding where Earth's water came from requires tracing this history backward across space and time. Astrochemistry provides the tools. It studies how molecules form, survive, and evolve in space from cold interstellar clouds to young planetary systems. In these environments, water appears early and persistently. Infrared observations reveal water ice coating dust grains in molecular clouds regions, only tens of degrees above absolute zero. Even there, water forms efficiently through surface reactions, allowing hydrogen to combine with oxygen. This means water predates planets. By the time a star forms and a disk of material gathers around it, water is already present, locked into ice and vapor. As planets assemble, they inherit this molecular legacy in varying amounts. The question for Earth isn't whether water was available, but how it arrived and how much was retained. Water is widespread in the cosmos, but the conditions allowing it to remain liquid over long periods are narrow. Temperature must fall within specific range. Pressure must be sufficient. The planet must retain atmosphere. Energy input must balance loss. These constraints define habitability limits. A planet too close to its star loses water to space through photodissociation and atmospheric escape. Too far and water freezes permanently. Too small and gravity can't hold atmosphere. Too geologically active and internal heating may drive volatile loss. Water's chemistry is forgiving. Its physics is not. Even where water exists, its state matters. Ice locked beneath kilometers of crust behaves differently from surface oceans. Supercritical water near magma chambers drives different chemistry than cold ice in shadowed craters. Habitability depends not just on water's presence, but on its accessibility and stability. This is where uncertainty remains most pronounced. Exoplanet surveys reveal many worlds within so-called habitable zones regions, where liquid water could exist on surfaces. Yet habitable zones aren't guarantees. They define possibility, not outcome. Planetary history matters. Delivery history matters. Retention matters. Geological activity matters. Water alone doesn't determine habitability, but without it, habitability is severely constrained. This perspective tempers enthusiasm with realism. The universe is rich in water but poor in conditions, allowing it to behave in ways life on Earth exploits. Liquid water persists on Earth not because water is rare, but because Earth occupies stable niche, allowing water to cycle without being lost. This niche is fragile on cosmic timescales. Earth's water inventory has likely changed. Some has escaped to space. Some has been locked into minerals. Some has been recycled through the mantle. Current oceans are snapshots, not permanent features. Looking outward reinforces this humility. Water's presence beyond Earth doesn't imply familiarity. Its forms, histories, and roles vary. Each environment reshapes water's behavior, revealing new aspects of already known adaptability. Astrochemistry shows water forms easily. Planetary science shows keeping it is hard. Between those facts lies the story of habitability. Water is widespread, ancient, resilient. Liquid water in stable contact with complex chemistry is rare. Understanding that distinction sharpens both scientific curiosity and perspective, as attention turns from familiar oceans to vast, varied reservoirs beyond each carrying its own incomplete history. If you want to know where something came from, sometimes the best clues are invisible, written into the atoms themselves. This is where isotopes enter the story. Isotopes are variants of the same element with different numbers of neutrons. Hydrogen, for example, usually has no neutrons, just a proton and electron. But there's a heavier version called deuterium with one neutron added, chemically. Hydrogen and deuterium behave almost identically. They form the same bonds, participate in the same reactions. But physically, deuterium's extra mass makes subtle differences. When water forms under different conditions, different temperatures, different locations in space, the ratio of deuterium to normal hydrogen varies slightly, but measurably. These variations act as fingerprints. preserving information about formation environments long after conditions have changed. Harold Urey, working in the mid-20th century, pioneered using isotopic ratios to understand planetary origins. His work demonstrated that these ratios survive geological processing, acting as chemical memory. By measuring deuterium to hydrogen ratios in Earth's oceans and comparing them to comets, asteroids, and meteorites, scientists can test different origin scenarios early on. Comets seemed like prime candidates for delivering Earth's water. They're rich in ice, originate from outer solar system, and impacts during early bombardment could have supplied vast quantities. However, measurements complicated this picture. Many comets exhibit deuterium ratios roughly twice that of Earth's oceans, a significant mismatch suggesting comets, like those measured, couldn't have been Earth's sole water source. Some comets show ratios closer to Earth's, others differ substantially. This diversity implies multiple water reservoirs with different histories. Attention shifted to asteroids, particularly carbonaceous chondrites meteorites containing water bound in minerals. These exhibit isotopic ratios much closer to Earth's oceans, suggesting water-rich asteroids may have contributed substantially. The emerging picture is mixed. Earth's water likely came from multiple sources delivered over extended periods, some inherited directly from solar nebula, some delivered by asteroids, some perhaps by subset of comets. None of these contributions can be isolated cleanly. This uncertainty isn't measurement failure, it reflects chaotic nature of planetary formation. Early Earth experienced countless impacts, material exchanges, episodes of heating and loss. Isotopic signatures were blended, altered, partially erased. What remains are constraints rather than certainties. Beyond Earth, isotopic analysis shapes understanding of water across the solar system. Mars shows evidence of ancient water loss. Through enriched deuterium content, lighter hydrogen escaped preferentially, leaving heavier isotopes behind. The Moon contains traces of water with signatures linked to both cometary and solar sources. Icy moons preserve water with compositions shaped by internal processing. Each body tells slightly different story. Beyond our solar system, water has been detected in protoplanetary disks, exoplanet atmospheres, cold interstellar space. Its presence is widespread, but form and abundance vary enormously. This raises important points. Water is common. Liquid water is not. Even where water exists abundantly, its state determines everything. Ice beneath kilometers of crust behaves differently from surface oceans. The distinction between having water and having accessible, stable liquid water is vast. Isotopic studies help reconstruct delivery mechanisms, but they also reveal limits. Some information is irretrievably lost to mixing and time. Ancient water on Mars may have a different isotopic signature than present traces suggest. Earth's earliest water may have been partially lost during moon-forming impact. Venus likely had water early but lost it through runaway greenhouse effects. Isotopes provide windows into past, but windows with limits. This leads to broader realization about planetary habitability. Water's presence elsewhere doesn't guarantee familiarity. Each environment, each planet, moon, asteroid interacts with water differently based on mass, composition, distance from star, geological activity. Water adapts to contexts, taking forms appropriate to conditions. Understanding water beyond Earth therefore reframes familiar questions. Instead of asking whether water exists elsewhere, deeper questions become: how does it behave? How long does it persist? Under what conditions does it remain accessible? These don't yield simple answers, they yield ranges, probabilities, limits. Isotopic fingerprints help constrain possibilities, tracing water's journey from interstellar clouds to planetary surfaces. But they're pieces of larger puzzles, not complete solutions. Water's cosmic story is one of abundance and scarcity, simultaneously plentiful as a molecule, rare in the specific stable liquid form that life exploits. That duality shapes both scientific questions and philosophical perspective as we contemplate our water-rich world and wonder how many others share that particular fortune. Let's return to Earth for a moment and appreciate something easily overlooked. How rare and fortunate our situation is. Earth sits in what astronomers call the habitable zone, the region around a star, where temperatures allow liquid water to exist on a planetary surface. Not too hot, not too cold, just right. But the habitable zone is only a starting point, not a guarantee. Many conditions must align. The planet needs sufficient mass to hold atmosphere. Too small and gases escape to space. Atmosphere is essential without it. Water either evaporates into vacuum or freezes solid depending on day-night cycle. Geological activity matters too. Plate tectonics recycle carbon, regulate atmospheric composition, and create chemical gradients supporting diverse ecosystems. Without this activity, conditions might drift toward uninhabitable extremes. Magnetic fields help by shielding atmosphere from stellar wind stripping. Mars, lacking strong magnetic field, lost much of its atmosphere and water over billions of years. Distance from star matters, but so does star type. Small, cool red dwarf stars are most common in galaxy, but planets in their habitable zones orbit close, so close they become tidally locked, with one face always toward star. This creates extreme temperature differences between day and night sides, potentially hostile to stable oceans. Larger, hotter stars burn out quickly, perhaps not giving life enough time to emerge and evolve. Our Sun, a medium-sized, stable yellow star, provides steady energy over billions of years. Earth's distance allows liquid water. Its mass holds atmosphere. Its geological activity maintains habitability through feedbacks we discussed earlier. All these factors align. Remove anyone and Earth might be very different. This is what scientists mean by a habitable niche, not just being in habitable zone, but having the right combination of size, composition, activity, and history to maintain stable liquid water over geological timescales. Such niches appear to be uncommon. Recent exoplanet surveys have discovered thousands of worlds. Many orbit within their stars' habitable zones. But how many have stable liquid water on their surfaces remains unknown. We can detect planets. We can estimate their sizes and masses. We're beginning to analyze their atmospheres. But determining whether liquid water exists and has existed long enough for complexity to develop requires more information than we currently have for most systems. This introduces humility. When we look at Earth's oceans and take them for granted, we're overlooking how many factors had to align to create and maintain them. Water delivered during formation had to be retained through violent early impacts. Atmosphere had to form and persist. Temperature had to remain within narrow range for billions of years. Geological activity had to continue, recycling materials and regulating climate. Any one of these could have failed, and Earth might resemble Venus to hot, water lost, or Mars to small, water frozen or lost. We inhabit a niche within a niche, a planet inhabitable zone that also happens to have the right properties to exploit that position. This perspective shifts how we think about water on Earth. It's not just a common substance we happen to have. It's the result of a specific, possibly rare set of circumstances that created and maintained conditions for liquid water to persist. Life in turn exploits this niche. Evolution has had billions of years to explore chemical possibilities in water-rich environments, generating extraordinary diversity. But that diversity depends on the persistence of the niche on water remaining liquid, accessible and abundant. Climate change discussions often focus on human timescales, decades to centuries. But Earth's habitability operates on longer timescales too. Over millions of years, continents drift, ocean basins open and close, ice ages come and go. Through all this, the habitable niche has held. Water has continued cycling, organisms have adapted, ecosystems have reorganized. This resilience isn't infinite. Push conditions too far and feedbacks that maintain habitability could break down. The niche could shrink or vanish. Venus may have once had oceans. If so, it lost its habitable niche billions of years ago when runaway greenhouse warming boiled away water. The planet crossed a threshold it couldn't return from. Earth hasn't crossed such thresholds yet. Our water remains, cycling through familiar paths: evaporation, precipitation, flow through rivers, storage in ice, transport by ocean currents, but the niche is contingent, not guaranteed. It exists because specific conditions align and persist. Understanding water, therefore, isn't just understanding a molecule. It's understanding the system's maintaining conditions, where that molecule can remain liquid, the planetary, geological, atmospheric processes that together create and sustain habitable environments. Water is common in the universe. Habitable niches are not, and we live in one. Shaped by water and shaping it in return. After all this uncertainty, disagreement, and open questions, it's worth pausing to say clearly, much about water is known with extraordinary confidence. The challenge has been distinguishing what's firmly established from what remains interpretive. So, let's be explicit. Some facts about water are experimentally robust, measured repeatedly using different techniques, across different laboratories over long periods. These don't depend on particular models or assumptions. They stand on their own. Water's molecular composition is certain. Each molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom in bent geometry. Bond angles, bond lengths, electronic structure, all known to high precision through spectroscopy, quantum calculations, and scattering experiments. No debate, water's polarity is equally secure. The uneven charge distribution within molecules has been measured directly and inferred through countless independent observations. This polarity underlies dielectric behavior, solvent properties, interaction with electric fields. Its existence and significance are not questioned. Hydrogen bonding is firmly established. Directional, transient attractions between neighboring molecules are supported by spectroscopy. Neutron scattering, thermodynamic measurements, typical strength and lifetime are well constrained. Even if collective behavior remains complex. Bulk properties, density, heat capacity, compressibility, surface tension, boiling point are known with extraordinary accuracy. Water's density maximum near the sea, expansion upon freezing. High heat capacity. These are repeatable measurements, not theoretical claims. Phase behavior under many conditions is well mapped. Multiple ice phases at different pressures, conditions for supercritical water. General phase diagram structure, all supported by decades of experimental work. Details continue refining, but broad structure is settled. Water's role in biological systems is strongly established. It acts as solvent for biochemistry, stabilizes charged groups, facilitates proton transfer, moderates temperature. These functions are demonstrated across biology, from enzymes to ecosystems. Where caution enters is interpretation. Knowing hydrogen bonds exist doesn't uniquely specify how they organize at any moment. In liquid water, knowing water has bulk properties doesn't uniquely determine microscopic arrangements producing them. Multiple models can account for same observations. This is where debate remains active. For example, consensus exists that liquid water exhibits short-range order. No consensus on how to describe that order most usefully. Some emphasize ice-like local structures. Others emphasize density fluctuations or network connectivity. Each approach captures aspects of reality. None has exclusive claim. Similarly, agreement exists that water near surfaces behaves differently from bulk. Molecules near membranes, proteins, or minerals are more ordered, less mobile. The extent, stability, and functional significance of this structuring remain under discussion. Scientific discipline doesn't require all questions be settled. It requires clarity about which claims are supported by direct evidence and which depend on interpretation. Water science maintains this separation carefully. When measurements are robust, they're treated as such. When interpretations are provisional, they're labeled accordingly. Disagreement isn't smoothed over, it's documented, explored, constrained. This prevents confusion between uncertainty and ignorance. Unresolved questions exist because foundational measurements are so solid. Basic facts aren't questioned. What's questioned is how best to connect them into unified explanatory framework. This is important distinction. Scientific progress often involves moving from description to explanation. Water has been described in extraordinary detail. Explaining how all descriptions fit together is remaining challenge. Meanwhile, water-related science remains highly reliable. Engineers design systems based on water's properties with confidence. Climate models incorporate its behavior successfully. Biologists depend on its chemistry daily. None are paralyzed by theoretical debate. They operate on what's clearly known. At the same time, researchers remain careful not to overextend conclusions. Claims about new phases, hidden order, or universal theories of liquid water are treated cautiously. Evidence is weighed. Alternatives are considered. This balance between confidence and restraint is strength, not weakness, reflecting understanding that some systems demand layered explanations. Knowing where certainty ends is part of knowing clearly. So what remains genuinely open? Not as loose ends waiting to be tied up, but as structural questions arising from how the system behaves. First, there's still no universally accepted microscopic description of liquid water explaining all macros. Copic properties simultaneously. Many models reproduce some properties well. None reproduce all without compromise. This isn't accident. Water exists in densely interacting state where molecules are close enough to influence one another strongly yet mobile, enough to rearrange constantly. A unified theory question remains open, whether liquids in general can be described by frameworks like those existing for solids or gases, or whether liquids require system-specific approaches. Some researchers argue liquids may resist unification by nature, requiring descriptions tailored to specific interactions. Others remain cautiously optimistic, pointing to advances in soft matter physics where concepts like emergence and universality classes help organize complexity. Second, the nature of local order in liquid water remains debated. Consensus exists that structure exists. No consensus on how to characterize it most meaningfully. Some descriptions emphasize tetrahedral arrangements resembling ice fragments. Others emphasize density fluctuations or coordination numbers. Some treat water as a mixture of locally distinct environments that interconvert. Others argue such distinctions impose artificial categories on continuous distributions. The question isn't which is absolutely correct, but which is most useful for explaining specific phenomena, and usefulness may vary by context. Third, water's anomalies cluster together in temperature-pressure space, but underlying reasons for clustering remain debated. Are anomalies manifestations of underlying critical point at inaccessible conditions? Or do they rise from smooth shifts in local structure without sharp transitions? Evidence exists on both sides. None is decisive. Fourth, scale cupping remains incompletely understood. How do molecular rearrangements propagate into mesoscopic and macroscopic behavior? How do local fluctuations influence bulk thermodynamics? How do short-lived hydrogen bond networks give rise to long-lived properties? These questions sit at intersections of dynamics and thermodynamics, regions where traditional tools still evolve. In biology, water's role inside cells is established broadly, but details of how intracellular water participates in organization, transport, and regulation remain under investigation. Degree to which water structure influences biological function isn't fully settled, nor likely captured by single answer. Again, this is structural rather than accidental. Cells are heterogeneous, dynamic, crowded. Water within them reflects the complexity across all these domains. One theme repeats: unresolved questions don't point toward hidden secrets waiting to be uncovered. They point toward limits imposed by complexity, interaction, and scale. What's missing may not be facts but forms of explanation, matching systems' nature, limits of knowledge. Here aren't barriers to progress, their boundaries shaping. What kind of progress is possible instead of closure? Water science advances through constraint. Models become better bounded. Interpretations become more precise. Domains of applicability become clearer. The field doesn't drift, it converges slowly. Not toward single picture, but toward clearer map of what can and cannot be said. This is different kind of maturity. Understanding water may never culminate in single unifying equation or theory. It may culminate in structured understanding of regimes, mechanisms, and limits. Such outcome wouldn't diminish science, it would refine it. There's a particular kind of humility that emerges from studying water, not the humility of ignorance, but the humility of recognizing limits even in deep understanding. Water demonstrates that knowledge doesn't always move toward neat completion. Sometimes it moves sideways, outward, deeper, all simultaneously. Measurements become more precise. Models become more sophisticated. Explanations become more careful. But closure remains out of reach. Not because something's missing, but because the system resists compression into final summary. This is where scientific humility becomes strength, not weakness. Humility doesn't mean uncertainty about facts. Facts about water are among the most reliable in science. Its molecular structure, polarity, hydrogen bonding, bulk properties, role in life and climate all known with extraordinary confidence. What humility recognizes is difference between knowing properties and fully unifying them. Water sits at intersections of many scales. Electronic structure influences hydrogen bonding. Hydrogen bonding shapes molecular networks. Networks influence thermodynamics. Thermodynamics feeds into planetary behavior. No single level governs rest. Each participates. Because of this, explanation becomes layered rather than final. A model may explain water's density anomaly. Another may explain dielectric behavior. Another may capture dynamics under pressure. None are wrong. None complete. Science advances not by pretending partial views are final, but by holding them together honestly. This is what makes water valuable case study. It reveals limits of reductionism without rejecting it, shows how collective behavior can emerge from simple components without being reducible to them, demonstrates complexity can be lawful, reproducible, measurable without being simple. Water teaches restraint, encourages saying clearly and confidently what's known and just as clearly what remains open. Unanswered questions aren't always temporary gaps. Sometimes they reflect problems' shape. This doesn't weaken knowledge, it strengthens it. When science acknowledges limits, it avoids false certainty. When it distinguishes measurement from interpretation, it stays grounded. When it accepts some systems demand multiple descriptions, it becomes more accurate, not less. Water studied across centuries and disciplines continues rewarding this approach. Each advance sharpens understanding while revealing new structure. Each refinement clarifies behavior without exhausting it. This isn't unfinished story waiting for final chapter. It's stable, evolving understanding that grows by constraint rather than conquest. To know water well isn't to hold it still, it's to understand how it moves, interacts, resists simplification. And in that understanding lies a lesson about knowledge itself. Completion isn't always the goal. Sometimes clarity is enough. So where does this leave us, lying here in the quiet? Thinking about water, we started with something familiar, something in a glass, in clouds, in cells. Something so ordinary it disappears from notice. We discovered it refuses to be ordinary once you look closely. 2 hydrogen atoms, 1 oxygen atom. Simple ingredients producing behavior that spans from quantum mechanics to planetary science. From picosecond fluctuations to billion-year climate cycles. From individual molecules to global systems. Water taught us about many body problems. About how cooperation creates properties that individual components don't contain. About emergence, complexity, and the limits of reductionism. It showed us that familiarity can hide depth, that the everyday can contain infinite layers. We learned about hydrogen bonding, weak individually, but powerful collectively, creating networks that flicker into existence and dissolve faster than thought. About polarity that makes water responsive, sensing and reacting to its environment. We explored anomalies, ice floating, heat being absorbed patiently. Expansion when cooling near freezing. Properties that seem wrong but make Earth habitable. We ventured into extremes, supersonic ice. Multiple crystalline phases. Water under pressures that crush ordinary intuitions. We saw water's role in life, not commanding chemistry but enabling it. Providing permissive environment where complexity can explore and persist. We confronted limits, the moving target of measurement. Disagreeing models, unresolved questions about unification. Not failures, but honest boundaries of current understanding. And we placed water in cosmic context, widespread but rarely liquid. Common but precious, abundant yet contingent. Through all this, one theme emerged. Water is not one thing. It's a system with many faces, each arising from context, each real, each part of larger whole that resists final summary. Understanding water means accepting this multiplicity, holding certainty and uncertainty together, appreciating what's known while respecting what remains open. It means seeing the extraordinary hiding in the ordinary, the complex within the simple, the unfinished within the deeply studied. And perhaps that's the most important lesson water teaches. Thank you for taking this journey with me tonight, for letting these ideas wash over you like water itself, sometimes clear, sometimes mysterious, always present. If you found peace in this exploration, if you learned something that sparked quiet wonder, I'd be grateful if you'd leave a like. It helps others find this calm space where science and rest meet. And if you'd like more nights like this, more stories that blend curiosity with tranquility, more journeys into the beautiful complexity hiding in everyday things, please subscribe and turn on notifications. This is just one of many stories waiting to be told. Share this with anyone who might appreciate it, anyone who loves science, who struggles with sleep, or who finds comfort in understanding the world more deeply. In the comments, I'd love to know, what surprised you most about water tonight? What will you think about differently next time you pour a glass or watch rain fall? And now, as your eyes grow heavier, as your breathing slows, let yourself drift. Let these ideas settle like sediment. Let water's story become a gentle current carrying you toward rest, from wherever you are. Whatever water is near, I wish you peaceful sleep and curious dreams. Good night.